Good morning, ladies and gentlemen. Okay, thank you very much for coming to this Sunday morning workshop. And I'm sure every one of you are watching the football last night. And yet again, you keep going for another 4 hours or so. And I can assure you, today's workshop will be just as exciting as the football match. Okay, so this morning we have 2 sections, and one in water, one in forestry. Before we start the 2 sections, we also have our distinguished speaker here today, Professor Charles Ng, will give the sort of keynote speech, keynote lecture this morning. Charles is the Vice President of the Hong Kong University Science Technology in our Guangzhou campus, which was opened in September this year. He's also the Dean of our graduate school in HKUST. He is the CLP Holding Professor of Sustainability and Chair Professor in the Department of Civil and Environmental Engineering here. Now, he has many awards. I just name a few. He's received the 2018-2020 Hong Kong Institute for Engineer Best Geotechnical Paper Award, Tedford Premium Prize from the Institute of Engineer, Henry Adam Award from the Institute of Structural Engineer. In mainland, he has been received National Natural Science Award, Science Technological Achievement Award, Scientific Advancement Technological Award. So it's too many of them already. He already told me to stop. So without further ado, I would like to invite Charles.
Good morning, everybody. And thank you, Jimmy, for your kind words, because he's my good friend. So he just intends to add more and more. I think I better stop. And I appreciate everybody to come here this morning, especially Sunday early morning. Thank you. And the title of my presentation is Analysis and Design of Debris Flow Resistant Barriers. And I must acknowledge my team members, including Karen Choi and Haifeng, Sunil, and Julian from GEO. And they have done all the work. I just do the talking. So don't put difficult questions to me. And also, I would like to acknowledge the funding source, which is from Research Grants Council. And here are contents of my planned presentation. And first of all, give a little background, and then current design approach. Then will be followed by our new analytical framework. And in the interest of time, I will not go to detail on that. But I will show you some physical model tests to verify our proposed and new design guideline. And of course, by doing so, I will show you the comparison between what we measured and what the prediction from our new analytical framework. And finally, I'll give a very brief design recommendation. So to start with, some of you may have seen this video yesterday before, but in case you haven't seen it, so what's debris flow? So this is unfortunately quite common, happen around the world.
왼편 우면산 쪽에서 엄청난 양의 토사와 물이 쏟아집니다. 바로 앞에 있던 차량들이 순식간에 사라졌습니다. 일촉 즉발의 순간, 여씨는 급히 제동장치를 밟았고 토사가 유리창에 튀었지만 차량이 휩쓸려가는 것은 간신히 피할 수 있었습니다.
Right. And actually, in Hong Kong, this type of failure is the number one threat to our society. And this type of failure also very vulnerable to climate change. Okay, and when there's enough water and initiate the failure, then just keep going and can have run out in terms of miles. Okay. And GEO, actually yesterday, GEO also mentioned they talking about natural terrain, essentially talking about that type of failure. Okay. And around the world, using different methods to protect the general public, and typically using barriers. And if I may just summarize two major types. One is a rigid barrier, which you can see on the left-hand side, okay, and on the right here, gradually, actually, I'm keep promoting using multiple flexible barrier, okay, because the rigid barrier you can see is very difficult to be blended naturally with the natural environment, okay, but flexible barriers, and when the tree grow up, okay, then easily can blend nicely with the environment. But in order to increase the resistant capacity, then has to be multiple instead of just one. Okay, and the big one. Traditionally, you put a big one at the bottom of a hillside. Okay, but which I'm sure you agree is very ugly. Okay, and use a lot of carbon. Okay, but usually multiple ones in some way we stop the debris or we decelerate debris right from the start. Okay. Then we reduce the design capacity down at the bottom. But design of this type of barriers, no matter whether it's rigid or flexible, actually in our profession, maybe not in yours, in our profession, still quite empirical. Okay, and that's all the research about what I'm going to describe to you. So I will not go into too detail of this, but just give you some idea. So for single barrier, then typically use this equation, so-called hydrodynamic equation, consider two parts. One is a dynamic part, one is static part. And I'd like to draw your attention is this alpha, okay, called a dynamic impact coefficient, which has been subject to a lot of research and also debate. And if you just look at this table here, ranging from Canada, mainland, and Hong Kong, and Italy, and Japan, and Switzerland, you can see they are all different values for alpha. What does that mean then? That means highly variable, uncertain, okay, different research or different country, they have different approach. Okay. And in Hong Kong, we use 2 for flexible barrier and 2.5 for rigid barrier. So now, today I wanted to share with you is how can we scientifically determine alpha, okay, for design of single and multiple barriers. The key word actually is multiple. That's why I highlight in blue there. Okay, to design for single barrier, relative is okay, but when you come to multiple, the problem starts. And actually, about 2 months ago, we means UST, we conduct a so-called Classic A Prediction Symposium, meaning we invite everybody on the planet to predict, okay, using whatever tools they want to do to predict alpha, and it's a blind test. Once they have submit their predictions, and we did a test and then compare, and the result scattered around substantially. Okay. But anyway, so today I want to introduce you to how can we determine alpha, especially for multiple. And conventional design, and this is widely used nowadays in Canada, for example, or in many countries, is considered static in the sense each barrier hold the same amount of volume, and also the barrier design against the same maximum impact force. Okay, and which is obviously not sensible. Okay, because it doesn't consider energy energy loss when the debris overflow the first one and then second one, and then landing also create a lot of energy loss. That's basically designed as a just like wish in place material. Okay. So again, is how can we scientifically determine each maximum force acting on the barrier and also the spacing. Now spacing is very important. Just imagine if they are too close, that means the second barrier is no in action. But if they are too wide, then the debris come down also accelerate. So I think that is the optimum spacing is also the key. Okay, so let me just quickly introduce our theoretical framework. Okay, so we consider three components. Number one is impact, the barrier, and then when the debris keep accumulate and then overflow, then we also consider the overflow path. Okay, and then finally landing. And landing obviously will have energy loss. Okay, and then once you land, you can continue to accelerate. Continue to move, not necessarily accelerate, but you continue to go. Okay, then hit the second barrier. Then what are you going to design for the second barrier in terms of alpha, let's say? So this is a challenging part. And then if you overflow again, okay, and how about the third one? Okay, so those are a series of quite challenging issues. If you're interested, can be discussed. Anyway, so we concentrate on those three components, if you like. So first of all, is the impact, and we modify what the hydrodynamic equation before I show you, and we allow for the flow process to consider the flow process change over time. Okay, that's equation 1. And then for equation 2, when the debris coming in, okay, with a velocity v and the thickness h0, okay, then we consider the climb up of this path allow for energy dissipation, okay, and also friction loss. So in other words, we consider the two components. One is friction loss, the other one is converting from kinetic energy to potential energy. So they come out with equation 3. And I will not go to detail, but I'd like to draw your attention. Okay, once we got equation 3, we can put back to equation 2, then we get this VD. Okay, that's what we're interested in. Okay, later on I will show you how does it work in terms of design. The second part is consider overflow. Okay, and we assume the debris coming in and then overflow and to a distance. Okay, and maximum overall distance, of course, we make certain assumptions. Then we can come up with an equation 4. Okay, so we can calculate how far the debris can reach the floor. And that's equation 4. Just remember the equation number that we do. No need to go to the detail. And then after landing, okay, hit on the floor, then what we are interested in is to find out the velocity component VI. Okay, means landed and continue to go. That's why we're interested in, because we want to know how are we going to design the second barrier. Okay, what force should we design against? Okay, so we're interested in VI, and then we define a term. Okay, and see how the ratio between the two universities. So velocity, not university. Okay, I'm still awake. I'm not awake yet. Okay, anyway, and so that we can put up equation 5a, and by equation 5a, unfortunately, it has to have an empirical number. Okay, and this is to account for the energy loss due to friction, which we don't know much. Okay, so by the way, so equation 5a or equation 5b is something we want to sort of verify through experiment. Now, after a very quick introduction about our theoretical framework, then we'll go to modeling. Okay. Now, debris flow is quite different from traditional landslides. It's scale dependent. What you can see is from the dimensionless group here. Okay, the key one for time, and stress, and also viscosity, they all relate to the thickness H, okay? 3-dimensional groups. And of course, we can carry out field tests, but field is very expensive, difficult to do, okay? And of course, ultimately, we will do the field tests later, okay? Then we start with modeling, okay? Because that modeling in terms of in the lab and also in our centrifuge. So here just a summary table of different scale of physical tools available to us to do the experiments. For example, in HKUST, we have a 5-meter long flume holding capacity 0.1 cubic meter, and this comparison with other locations. And we also have a geotechnical centrifuge. By scale the gravity up, say 15, 20 times, then we are able to simulate up to 170 cubic meter. This is already converted into prototype. And then we also have, later on, you also have a 28-meter long flume, which is funded by our joint project, Area Excellent Project. And then nowadays we are collaborating with the Chinese Academy of Science, building one of the, actually the largest 172-meter long flume in Kunming. It's being under construction. Hopefully by the end of, not by summer, hopefully will be completed. Okay. But before we see before you use the result from the 172-meter long flume, we show you some 5-meter and also from 28 meters long flume tests. Now, small is beautiful sometimes because you can very detailed study the mechanism. When you go to the big scale, actually, in some ways, it's quite difficult to do the analysis. Okay. Okay, so this is our indoor. Indoor meaning we can control whatever way we like, okay? But different from in the field, then you got to be friend of God, okay? And anyway, so we put down, we have a hopper here containing the debris, okay? And then when we open the gate, the debris will flow down and then can be measured in terms of run-up height and also in terms of velocity. And then if the debris overflow, then we do the same thing. So in the lab, we can obtain whatever data we want. And now, in order to investigate, okay, what should be the optimum height of each barrier, so we conduct a series of tests. But I guess I don't have time to go into detail on that. So I just show you one of our tests. Okay, just to give you an idea. Now the debris coming from the right-hand side, okay, overflow, and then land, and then see the second one, okay, and then overflow. And then you can imagine, you can go on and on, okay, depends on how many we put, and also depends on how big the debris volume to start with, okay. Then that would depends on many factors. Okay, so after seeing 5 meter long, let's see 28 meter long. So this is we collaborate with University of Hong Kong, and we built a 28 meter long flume and a 2 meter wide, and at the Katori Center there. So let me show you a video quickly.
The state-of-the-art 28-meter-long flume is one of the largest facilities of its kind in the world for studying landslide and debris flow problems. This facility was spearheaded by the Hong Kong University of Science and Technology and supported by the Research Grants Council of Hong Kong. The channel is 28 meters in total length, 2 meters in width, and 1 meter in depth. The flume can model a maximum volume of 10 cubic meters of debris flow. This unique facility was purposefully developed for studying the scale-dependent interaction between debris flow and multiple flexible barriers. For this project, a new instrumentation cell has been developed to measure the normal and shear stresses and changes in pore pressure. This instrumentation cell is installed at regular intervals along the base of the channel. In addition, unique instrumentation such as unmanned aerial vehicles are used to carry out 3D reconstruction of each test, and smart soil particles are used to investigate the mesoscopic dynamics within the flow.
Hong Kong is a very hilly city, resulting in about 300 landslides every year. And given the climate change, and people expect more bigger unexpected landslide will occur. Conventionally, people use a barrier to stop debris coming down and to hit the urban area. But the current design guideline is essentially for single barrier only. And this project is designed to verify our newly developed design guideline for multiple barriers. In addition, you can see.
Okay, so I think in your time, I just stop here. Now, when we want to compare our theory, then also we must make sure, okay, each test, they have some consistency. So we design our own mix of the debris. But we don't plot this from the air. Okay, we actually sample 30-something landslide sites in Hong Kong and then plot them in this graph and compare, and also plot debris flows in Korea, Japan, and Italy, and so on, all in this graph. And then we come up with our sort of the way you can see this red cross and in a box there. This is our sort of standard mix, if you like. And then we use this standard mix to do all our tests so that we can compare them, okay, scientifically. Anyway, and also for a design of flexible barrier, then traditionally using so-called brick ring. That's what you can see here. Okay, here's a before the debris happens, it's like circular shape, and once the debris hit the flexible barrier, then this deformed, and that means become cannot be reused. So we design our own and dual bilinear bricking system that enable us to reuse the so-called brick rings, okay, as many times as you want, okay, and also can be repeatable, and also we can adjust the stiffness of the tool inside these two brick elements as we wish. Okay, so now let me show you a video, actually two videos, okay, and this is a video putting on top of the debris, okay. So let's see the difference between with and without brick elements. So on the left-hand side are the tests you can see coming down from the top, okay, hit the flexible barrier, okay, and then you can see roll back, first of all run up and then we fed the wave back, okay. And the deformation is about 11% of the length. So now let's see the one on the right, okay. And this one is the barrier actually installed with our bilinear brick elements. So initially not much big difference, but if you watch here, okay, they start with a rollback mechanisms, dissipate a lot of energy. Okay, that's good news because the dissipate energy among the debris themselves. That means the design of the flexible barrier can be less costly. Okay, let them destroy themselves first. Okay. Okay, so I guess I've got to speed out a little bit. Okay, and then let's see the comparison between the measured and also the predicted values by our theoretical framework. I hope you still remember equation 2. Okay, so this figure here essentially comparing how effective of equation 2 or how good is equation 2. So what you are seeing, the plotting in the vertical axis is normalized height, okay, and the horizontal is a normalized one-up velocity, so that we can compare different scale. And just draw your attention, those are black triangle here are those measured from the 5-meter long flume, and the solid line here is the prediction from the equation 2. Okay. And then if we move up here, the red dots are the measure from the two-phase flow in a 28-meter long flume, and the dotted line here is the one calculated by equation 2. Now the upper one here, the square solid symbols here are all measured from the 28-meter long flume with water only. Okay, you can imagine that it's a mixture of solid particle and water. So the upper bound, in a sense, is water, if you like. Okay, so those are the water based on what a test on using water, and the dotted line here again is a prediction from equation 2. And I hope you agree, the prediction not perfect, but I think it's reasonable, at least from an engineering sense. Okay, but of course from physicists, they may say, "Wow, that's too bad." Okay, but from engineer, you get anything close to 10% is very good already. Okay. And how about overall distance? Okay, now overall distance again here. I use the same convention. Any measuring point is a dot. Okay, so the triangle, 3 dots, that means 3 tests from 5-meter long flume, and the dotted line, black dotted line here are the predictions, actually predicted line using equation 4, and then 3 red dots are same in the same flume, but with a different degree of an angle. And again, the red dotted line is the predicted line. And up here, okay, there are 2 tests in the 28-meter long flume. First of all, the calculated one is the one from equation 4, and this one here is the measured, and there's a pretty there's a quite high discrepancy. But when you look at the debris one, okay, then again there's a discrepancy, but I would say it's not too bad, and the debris is in solid, and the predicted the calculated one is an open circle. But fortunately, all the predicted ones is higher than the measured ones. That means if we use it for design, then we are on the conservative side. Okay, if the other way around, then I think we're in trouble. Okay, and of course, the reason why of this involving in the assumptions in the calculation. Okay, and we are reasonably happy, but not completely happy, but reasonably happy in terms of engineering design. Then how about the landing part? Okay, again, all the black dots are the measurements, and also including the red dot also measurements. So if we assume alpha, so our R equal to 1, okay, then we give us a so-called upper bound curve, okay. And if you want to get a best fit curve, is R equal to 0.9, okay. So once we can determine this from experiment, okay, then we can work out CR. Once we work out CR, then we can know what is VI. That's what we need for the calculation of the second barrier or the third barrier. Okay. And then we verify this, okay, again, based on measurement about once we say we use R equal to 1, and use the upper bound, it's okay for assuming no friction loss. But what should be the CR actually? Then we we do the calibration again, okay, based on experiment, and the measured ones are shown in the red, and then the calculated one from equation 2 and equation 5 using CR equal to 0.7, then will give us a very nice match and slightly overestimate, which is good. Okay, that's what we want. So we can conclude we use CR 0.7, R equal to 1 for our design. Okay, so let me jump to the design recommendation, and the vertical axis is normalized impact force, and horizontal axis is in one way to describe the debris flow characteristics is full number, and the two dotted line here are the design calculated curve, if you like, from using K equal to 1, alpha equal to 2.5 for rigid barrier, and that's a GEO's design guideline, and then flexible barrier, okay. And Julian and Raymond, yesterday, Raymond was here. Okay, so this is the design guideline. And then based on our tests for rigid barrier, okay, we propose actually alpha can be reduced to 1.5 instead of using 2.0. And for flexible barriers, okay, we propose can use alpha equal to 1.0 because those two newly drawn lines actually are on the bound all the relevant experimental data from what we have, and also we collect some data from other researchers. Now the interesting part is the second barrier, okay. And before we cover the experiment or theoretical work, there's no design, explicit design value for use for the second barrier. We always use the same as the first one, okay. Now, so talking about the first one, so this is the first one we propose, okay, for rigid barrier 1.5. But when you come to the second one, okay, actually can be further reduced if we allow for the energy loss, friction loss, and so on. So the alpha can be 1.0. Okay, so and this one, I believe nowadays, GEO also consider in their design guideline, certainly, and being considered in other places. And hopefully they will do more work, okay, to further improve. And okay, just a quick summary, okay. And I didn't talk about anything about basal clearance, so not worry. And so here's a list of numbers for different conditions. But the key is now we have a vehicle, if you like, or tool to allow for the design of a second barrier. And here just the quick summary. Okay, for multiple barrier, the overall distance can be conservatively. The important thing is conservatively estimate using equation 4. Okay, although it's not perfect, but it's on the conservative side. That's good. And then the landing factor. Okay, CR 0.7 R equal to 1 also can give a conservative estimate of flow velocity before the second barrier. Okay. So with that, I will say thank you for your attention. Thank you.
Okay, thank you very much. Thank you for Charles making our hilly city much safer. Is anyone would like to ask any questions before we go to the next section? Any burning questions? Yes.
Yeah, I want to know, because you say all the current design is single barrier. How do you anticipate this design will change the implementation of barriers in Hong Kong?
Right, thank you. The current, I would say the current approach, not just in Hong Kong, around the world, in the past, using single barrier mainly. Why? Because they're easy to construct. Okay, and after, if there were debris hitting on the barrier, they clean up is easy, right? Because it's at the bottom of the hillside. But nowadays, and because of we human beings don't like big concrete, stop there somewhere, right? So we like to see natural environment. So that's why around, not just Hong Kong, around many countries, they start to think about, can we use something on top of the mountain so that people cannot see easily, okay? And also, construction should be
much cheaper.
Not that difficult. If you imagine build a big concrete up there, it's difficult. But if you use a flexible one, it's more easier. Okay, so start to build and use a multiple. But the problem is how to do the design. Okay, and actually I talked to two suppliers in the world. I say, how do you design the multiple barrier in terms of force, in terms of spacing? Or he said, that's easy. Use the same number. Then of course from the manufacturer supplier, they of course, right? Then I didn't say it. I just think of course you suggest use the same so that everything can be big. That means they can have big income.
Yeah.
Right.
Twice or 3 times.
Yeah. Okay. So, but unfortunately, or fortunately, okay, I would say unfortunately, in a sense, people haven't since about. Actually, we search around the literature, okay, and there's no literature around to guide how to design the multiple barrier. That's why we got the RGC funding, okay, and to support us to do the research, okay. So hopefully, we'll see more, okay, that's how flexible barriers, and then nicely blend with the natural environment so the residents will not see them easily, okay. And also together with what Raymond said yesterday, can have a smart sensor mounted on the barrier so that when they hit it, then GEO will know immediately, okay. And I think that's our announcement. And I don't know whether I answered your question completely. So, but the work hasn't finished yet because we only verify to the second barrier. Then how about the third one? Okay. Then I think there's something, because there will be further energy loss. Okay. And also what's the optimal spacing? And then there's something.
Okay, maybe the last one, yeah. Sui. Okay,
Thanks, Charles, for a very informative talk. So I'm very new to this area. So I was wondering, how do you know beforehand where to install the barriers? So which area actually are more likely to have landslide or the problem?
That's an excellent question in a sense. Okay, a friend of God. That's the answer. No. No, and we have an excellent engine geologists. Okay, so they would normally when we do a design, we involve engine geologists. They would, I wouldn't say they predict, they estimate. Okay, where the likelihood debris flow will happen. Okay, and of course some sort of obvious factors can be considered. For some slope angle, okay, soil type, rock depth. Those are the obvious ones. But even you can compare those different locations, the obvious factors may be very similar, but still you cannot tell which one will happen. That's why if you see after this meeting today, if you go out to Tuen highway, or they put everywhere, right? Because they don't know where will happen. Okay, even more important, when will happen. Okay, just like earthquakes, we have a very good sociological experts, but they can predict where and magnitude of earthquakes. But the problem is they cannot predict when. Okay, so the same issue here. Okay, we don't know, unfortunately. Okay, but we based on what the knowledge we have, and to protect the major city. But funny enough, if you think about in Canada, for example, in most cases, they don't care. Why? Because they are far away from the residential areas, far away from the roads. They don't care. They don't need to care, but we have to. In Hong Kong, it's such a small city and a congested one. So that's why different sort of background, different way to thinking about the design.
Okay, so with that, okay, thank you very much for Charles for this keynote talk. Okay, when will happen? Of course, the landslide will happen typically with excess water. Okay, so that's why we come into the first section of today's various talk. Okay, excess water challenges. Okay, the first speaker of this section is Professor Chai from the Division of Environmental System Analysis School of Environment, Tsinghua University. Okay, please, Professor Chai.
Okay, it's my pleasure to be here. Just during my Hong Kong visit, there's a conference here. So recently I mainly work on the Smart City, do some basic research, also some consulting works for the central government and some municipal government for Smart City. So I would like to use this situation to explain some activity, also the problem challenge we face during the Smart City construction. So I will have several contents. First, the background. I think because of the time limit, I did not spend more time on that, but just several figures. First is about the global trend of urbanization. From this data from the United Nations, we can see in Europe, in the North America, or Oceania, they have a developed country, so they have a higher urbanization. In Africa and Asia, comparatively, we have a lower urbanization, but we can see in recent years, we have a rapid speed. So urbanization, we know they can give us a lot of positive impacts on social life. However, they also give us some negative impacts, especially on the world environment. So we can see from this, compare with natural ground cover and the higher impervious surface, about the evaporation decrease a lot. Also, the infiltration decrease a lot. So the runoff increase a lot. So we can say in the natural ground cover, in average, the runoff is about 10%. But in the high pervious urban areas, the runoff increased to 55% in average. So this give us a lot of problem. So here are some photos about the urban flooding. You not only in China, but all over the world. So you can see there from Houston, India. Last year in Zhengzhou, many people died because that's flooding. Also, the last one is in Beijing. You can see some people on a boat. Actually, it's not river, it's a highway. You can see the bottom of the bus. So that is a big event that at the end of 2012. So because this event, the manager, also the experts discuss about that. And in the end of that year, so central government to propose the Smart City initiative. Besides the flooding, we also have the pollution problem. So for in the urban runoff, so most traditional pollutants exist, such as the organic, also the nutrient. But some toxic compounds can be also found in the urban runoff, such as some heavy metal, also the POPs. So two pictures I took take a different time. One, you can see the very black river. It's a Foshan city, just in Guangdong province. at that time, the wastewater treatment plants is not be treated, so the water black all day. So after we have constructed the wastewater treatment plant, so in dry time, the river is high quality, but during the stormwater, we still have the problem. So, the left picture says the overflow, combined overflow. So in the raining season, so still have this kind of problem. Also, we facing the ecological degradation. So, based on the research, if a worksheet, the impervious rate is larger than 55%. Usually, the natural system cannot afford their ecological quality. So, in this, because urbanization, they impact the hydrology, water quality, and habitat, and then they influence the ecological condition. So this is, however, in China, we still in the period of rapid urbanization. So from this figure, we can see from 1952 to 2008, the urbanization increased a lot from nearly 13% to nearly 45%. And in this year, in 2019, it's reached more than 60%. So we can imagine the urban problem will be severe if we're still in the current development model. So we need to find the solution. So in this context, in China's central government promote the smart city concept. So formerly in Chinese government document is first to document in end of the 2013. In the report by President Xi Jinping, in the report it said the priority should be given to rainwater detention and storage use on-site natural approach when upgrading the urban drainage ability, by which we could to build the smart city capable of store, infiltrate, detain, and treat runoff naturally. So this is the first official document in China. So compare with the traditional approach, the philosophy is different. In traditional, we call that is the rapid drainage approach. In that time, we think the stormwater is a bad thing. We need to get rid of them as far as possible, as quick as possible. But in the smart city approach, we think that is valuable resources. We should slow it down, clean it up, or soak it in. So compare with these two figures. So for the smart city, we need to more infiltration, more collecting for utilization, and increase some evaporation to less the discharge. So the concept of the smart city, we have 4 practical objectives. No ponding in light rain, no flooding in heavy rain, no black and odor urban river, also mitigating the heat island effect. So it is now the urban developing paradigm. So which to enable all the land use, building, road, green space, water system, and other to play their roles to strengthen the urban planning and development model. So the technical road for smart city construction is, we call that the source reduction, process control, and systemic development. So we think on the site, all RID facilities should be used on site, and then we consider the traditional green infrastructure and the green infrastructure, also the blue infrastructure together. And we need to think that in a worksheet scale, integrated approach to do that. So this is how to organize the smart city construction. So the main responsibility is the city government. So the city government usually they organize an office or committee, including different agencies, and then to do the planning, to do the overall planning or special planning. This is a technology planning. And for the design, construction, operation, the government encourages the PPP mode, public-private partnership. So here is about the roles. The central government is a promoter. Local government, designer, planner, construction is the implementer. Also, the maintainer and public should be the protector. So different stakeholders have their different roles in the smart city construction. So here show several works, different stakeholders, their responsibility. After the smart city initiative be promoted, so the central government have selected 30 national pilots, and the provisional government, they also select their own provisional level pilot city, about 100. So for national pilot, the central government will subsidize a certain amount of money. So they estimate they have a 1,000 billion yuan market for smart city. So a lot of company, they involve the construction of the smart city. And currently, the pilot is finished. And the government, also the experts, learn from them. So currently, we have from the pilot to demonstration. So in just last year and this years, the government have selected 45 demonstration cities around the world, around China, to do this kind of demonstration. And the smart city also attract a lot of attention internationally. So I just mentioned in the one of the magazine, the front story is about the smart city in China. Also in Nature, in Science, they also to mention the smart city concept. And I involved the organization of the two big conference. One is in Beijing, another is in Xi'an. To a lot of experts, also the manager attend that conference. Also, I mentioned that smart city also included in the United Nations UNESCO report. Is one of the case studies for the natural-based solution. So, however, we also have some barrier and challenge. So, first is resistance to the change initiative for traditional approach, because that is a different philosophy from the rapidly drainage to the smart city concept. So currently, all the planning, design, construction guideline is the traditional approach. How to change is a big difference, big difficulties. So this is one of the barrier. Another is we still have a limited technical for the planning, design, and assessment. So this is also the big limitation for that. Also, because the smart city construction needed the coordinate of the different agencies, government agency, different disciplines. So still lack of the close coordination among the agency at the local level. Also, how to quantification of the cost effective is also a problem. So currently, we still have a lot of challenge to overall. Financial is always a problem for this kind of the project, and education, training also the challenge. In our research group, we do some research, so I just very quick. So this is a Beijing Natural Science Foundation major program to do the spatial characteristics of the urban surface feature and to build a fitness assessment for the smart city construction. So we want to give the spatial characteristics of different underlying surface, and from the city scale, block scale, also size scale, give a different method to support the planning. Also, because there's many type of source control facilities, we call LID BMP. So how to select it suitable based on the local condition is also a challenge. So we just to develop a selection system based on the local suitability, also the effect and the cost criteria to rank the different the type to assist how to select the suitable one. And then based on that, we just select the software. After we select the suitable facility, we need to optimize the site and the scale of this kind of the LID BMP. So we do also this kind of work to do the optimization. And we do some evaluation based on the life cycle, including different different stage from the economic and ecological environment aspect to evaluate the source control facilities. And we currently just develop a database to including different kind of data, also the design perimeter. So with this, we also do a comparison with United States. So we do this kind of comparison. So also we do some work in Tsinghua University with a sponge campus. So because of time limitation, so quickly. So this is after the construction in Tsinghua campus. Currently it's the hot spot for the student or the public to come this area. And one of my students to use this study to get the research award from the ARSA. So calculation is we just mentioned that along the rapid urbanization, we have some negative impact on the hydrology pollutions. So smart city is one of the most important principle for the urban development, but we also face some challenge. A lot of barriers exist. How to deal this kind of things is very important and urgent. So I think we can do that together to solve this kind of problem. So thank you very much for your attention.
Okay, so thank you very much. I would like to group all the questions together until the end of this section. So maybe I would like to invite the, thanks, Professor Cha. Okay, let us, Professor Lu, currently she's not able to join us because she's going to join the AGU in the US. But however, she has made a video. Let us hear her talk on this clustering catastrophic weather event from India to China and to Canada. Basically, it's the whole North Hemisphere. With that, okay, let us show the video.
Hello, I'm Mengqian, an associate professor of hydrometeorology and water resources in the Department of Civil and Environmental Engineering at HKUST. I'm very thankful for the opportunity to present a recent study that is motivated by the clustering extremes from India to China to North America during the COP26 last year. I will also explain the important discovery of how the sequential extremes were actually shaped by MJO and La Nina and to form a new Asian-North American teleconnection. This is a collaborative work with Professor Wang Bing from University of Hawaii and also Dr. Lee from Central Weather Bureau in Taipei. Our paper just got published by NPJ Climate and Atmospheric Science. I hope you will find this talk interesting. by the end, I will also spend some time to briefly introduce other projects that our group is pursuing. Extreme events from South Asia to East Asia and then to North America clustered during the COP26 conference last year. The figure shows the precipitation of selected events in the clustered sequence in November. And it started in India and Sri Lanka with heavy precipitation and severe flooding, and then closely followed by the record-breaking snowstorm in Shenyang, in northeastern China. And then only in 3 days, Canada and the Pacific Northwest were heavily hit by record-breaking precipitation and severe flooding. Two events might be coincidence, but a sequence of extremes propagating from South Asia to East Asia to North America made us wonder if they are linked to each other. And more importantly, is this an indication of a new form of compound extreme events? To verify our hypothesis, we conducted a careful investigation to address these three questions. How are they organized? Are there conducive environmental conditions? And are there root causes? We think that these questions will lead to a deeper understanding of the origins of increasing collisions of extremes that we have witnessed in the past several years. Based on the locations of the clustered extremes over time in November, we divided the cluster extreme events into 3 stages. They are Indian extreme stage, East Asian stage, and North American stage. The figure shows the intraseasonal evolution of the atmospheric anomalies during these 3 stages. Now let's take a close look into the evolving environmental conditions. During the first Indian stage, it features a wet India, dry Philippines precipitation pattern. When we take a look at the upper level on the left, an anomalous South Asian high emerged with a center over the Indo-China peninsula, and the wave activity flux indicate that the wave energy propagated from Central Eurasia to Tibetan Plateau could favor South Asian high's northwest movement and development. As Indian convective heating can generate the upper-level South Asian high, and the wave energy propagating northeastward from the South Asian high strengthening the upper-level East Asia low, it means that the anomalous Indian heating may contribute to deepening the upper-level East Asian trough and intensifying the East Asia winter monsoon. At lower level, the suppressed Philippine convection shaped an anticyclone circulation, strengthening the southwesterly from Bay of Bengal to southern China, and we see an atmospheric river formed, transporting abundant water vapor from South Asia to East Asia, preconditioning the extreme precipitation over eastern China in the next stage. Also, a cross-Pacific wave trend emerged. As the South Asia high and East Asia low were strengthened, East Asia experienced a record-breaking snowstorm. At the upper level, it is apparent that a circum-Pacific wave train was established in this stage, consisting of the South Asia high, East Asia low, Okhotsk high, and Gulf of Alaska low. And then at lower level, the cross-Pacific atmospheric rivers persisted, continuously bringing warm, moist air to the west coast of North America. The third stage is characterized by severe flooding in North America. At this stage, the South Asia rainfall anomaly extends to Southeast Asia, and the upper-level South Asia high expanded accordingly. And the circum-Pacific wave train persisted and tightened, and then another new cross-Pacific subtropical Rossby wave train developed. And the subtropical wave train aligns quite well with the circum-Pacific wave train. So as a result, the cyclonic anomaly over Gulf of Alaska shifted southwestward and into the central North Pacific. Because of this, the Pineapple Express AR was established from Hawaii to the west coast of Washington State and British Columbia, and then continuously to feed the devastating rainstorms over Canada and northwest US. In fact, the cross-Pacific AR have been active since the beginning of November, making the west coast of North America prone to flooding with saturated soil. We named the circulation pattern organizing the extreme precipitation events as a new Asian-North American teleconnection. Our hypothesis is that the wet India, dry Philippines dipolar heating anomaly we saw since the beginning may have triggered these wave trains and sustained the cross-Pacific ARs. We conducted a suite of numerical experiments with an LBM. We specify climatological mean flows in November as the basic flows. We specify 3 types of heating patterns to mimic first the dipole heating pattern, and then the Indian heating only, and then the Philippine cooling only. By the experiment result, we can see that the dipole pattern excites a teleconnection pattern that resembles the observed circum-Pacific wave train. And although the North Pacific anomalies seems a little weak, okay, and then the wave energy generated by the Indian heating and Philippine cooling support the anomalous South Asia high and East Asia low respectively. And we find that the Philippine cooling contribute to the circum-Pacific wave train in the mid-latitude, similar to the one during the East Asian extreme stage. And then on the other hand, the Indian heating enhances the eastward subtropical wave train that crossed the Pacific. Then we ask who triggered the wet India and dry Philippines dipolar pattern. First, we find that in October, the Eun-soon index plunged to -1 degree Celsius. By November, a La Nina condition had firmly established. The negative SST anomalies covered the entire central and eastern Pacific. The La Nina condition installs an anomalous low-level quadrupole circulation pattern with a pair of cyclones straddling the Indian Ocean and double anticyclones over the western Pacific. The La Nina condition contributed to the setup of a wet India, dry Philippines anomaly pattern, but we find that the La Nina is not the only one. With the La Nina background, an MJO event also developed over the Indian Ocean in early November. And from the MJO index, it is clear that the MJO stalled over the western maritime continent for a long time in November. And a zonal ring belt is formed over South Asia, and suppressed convection is sustained over the Philippines as a result of the stalled MJO. So it is apparent that this quasi-stationary MJO also bolstered the dipolar heating anomalies over India and Philippines. And both the La Nina and MJO positively enhance the dipole heating anomalies. And when we compare the anomalous OLR strains, the climate mean anomalies is weaker than the intraseasonal signals. So we think that the MJO-induced convective anomalies are significantly more intense, especially over the Philippines. To summarize the interesting mechanisms we identified here, we can see that first, the equatorial SST gradients generate easterly anomalies and suppressing the equatorial western Pacific convection and enhancing the maritime continent convection. As a result, we saw a pair of symmetric low-level cyclonic circulations over Indian Ocean, which encouraged the moisture convergence to feed the anomalous South Asian rain belt. And likewise, the suppressed equatorial western Pacific diabatic heating and the anomalous easterly stimulate a pair of anticyclones. And this Rossby wave response enhanced the western North Pacific subtropical high and reduced precipitation near the Philippines. And then with reinforcement from quasi-stationary MJO, the dipolar heating anomalies are strong and triggered the cross-Pacific wave trains that formed a new Asian-North American teleconnection. So we conclude that this COP26 clustered extremes might be a new form of compound extreme and are organized by the Asian-North American teleconnection on the intraseasonal level. And then the wet India, dry Philippines dipolar diabatic heating fortifies the ANA steady connection by generating the two cross-specific wave trains. So the dipole heating anomaly is set up by the rapidly developed DELINA and bolstered by the quasi-stationary MGO. We believe this study provides a new perspective on future precipitation variability by emphasizing the clustering of extreme precipitation events with escalated compound impact beyond their simple addition. This is our recent work, and next I would like to take a few minutes more to briefly introduce other projects that we're working on. This is my hydromet team at HKUST. My students have different education background, from hydraulic engineering to atmospheric science to applied math and statistics and more. We are tackling a good suite of research challenges that pertain to climate change and water resources sustainability. Here is a snapshot of our current research focuses, from regional and global moisture recycling and transport to intensive moisture transport represented by AR, and we trace moisture advection and all the way to the places of their destination, and follow through the lifetime of moisture in the atmosphere. And we hope that we can have a better understanding of what are the steering mechanisms behind the atmospheric branch of global water cycle. And we also look at East Asia hydroclimate and hydrometeorological features, including monsoon annual cycle, subseasonal to seasonal features, tropical cyclone activities, and so on and so forth. And we look at natural hazard as independent hazard types, also collectively as some form of compound event. And lastly, the engineering components of our research lies in water resources cross-operation research and infrastructure and built environment sustainability. Such as one of our ongoing big project is about robust water infrastructure planning in the Greater Bay Area, and this is a collaborative project among different disciplines. Atmospheric moisture transport and recycling is certainly the heart of our research, as many applications and extensions are based on learned knowledge from water cycles and transport. From this illustration of our work's spatial temporal scales, you can see that our group is like working on a jigsaw, playing with different scales, trying to understand how moisture moves in the Earth system, steered and regulated by atmospheric dynamics and thermodynamics of different scales. We believe from atmospheric moisture transport and recycling to sustainable water infrastructure planning, every drop of water is precious. That is why we spare no efforts in pursuing a better understanding of the water and climate system while developing novel algorithms to identify AR and MCS, and also construct our own database about AR and MCS in the global and regional scales. We also do our diagnosis of Australian Asian monsoon system. Particularly, we love to investigate the complex interactions among processes of different scales. And then we also use a lot of data-driven approach, but I want to emphasize that although our analysis is data-driven, we always land on a deeper physical understanding. And lastly, we think our research could give back to provide a better predictability of extremes and also give information to support better future infrastructure planning and give rise to built environment sustainability. This is all of my presentation today. I hope there will be an opportunity to meet you in person and continue our discussion. Thank you.
Okay, so thank you, Professor Lu. You can see he's very cover many areas of water cycle. Okay, with that, I would like to invite Professor Xu. Yet again, I'd like to swap the talk a little bit because it's still on accelerated intensification of extreme rainfall at urban scale. And Professor Xu is from the Department of Environment and Sustainability here in HKUST.
Okay, thank you, Jimmy. Yeah, okay, good morning, everyone. So this work is done in collaboration with Professor Charles Ng, Professor Jimmy Feng, Alexis Lau, and also a few students of ours. So this is a part of the area of excellence work for slope safety. But of course, for my work, my background in meteorology, and we focus on precipitation. So, about the extreme precipitation, there are some conclusions, but there are also a lot of uncertainties. So previous work have already shown that actually the extratropical precipitation, we have more confidence in its prediction. So the figure on the left is showing you the precipitation for the past, the observation, that's the black line. So the blue line is the simulation from climate models, which is not bad. And the red line is showing future prediction for the 80 years later. So you can see the red line shows that in tropical region we get more increase in precipitation. But you can also see this gray shading, which is showing you the uncertainty. So these are all based on the previous generation of climate models from results of about 30 of them. And then on the right-hand side, the figure is showing you the sensitivity. So that's the fractional change. So that's the fractional change, and you can see overall the extreme precipitation here is defined as the 99th percentile of precipitation, and then you can see the sensitivity is about 6% per K. That's the blue line here. But then the thing I really want to emphasize is this uncertainty range in the tropical and subtropical region. Again, this shading is showing you how different those 30 climate models predict about the extreme precipitation sensitivity. So in extratropics, actually, we are pretty confident that the sensitivity is about 7% or 6% increase or per degree of warming. So that means if you increase global mean temperature by 1 degree, then precipitation increase by 6%. But in the tropical region, you can see the uncertainty range is between 2% per K to 9% per K. And particularly for tropical cyclone, for typhoons, there were a recent paper by international experts in typhoons, and their prediction is that the change is between 3 to 11% per K. So that's the currently internationally agreed range, but that's still a large uncertainty range. So our work is trying to get more confident prediction about the extreme precipitation in the South China region. So this is, we are in the subtropical region. We also get a lot of precipitation from convective weather. And the convective weather is really difficult to capture in coarse resolution climate models. So the global climate models usually have a 100 kilometer grid spacing. So that's the grid cell of their simulations. But then in that resolution, you cannot resolve the details of the weather system in this region. So we used the 1 kilometer resolution to represent the weather system in the South China region. And then we selected more than 60 cases of extreme precipitation, half from the present weather and half from the future warmed climate. And then we compare them and see how their intensity change in response to global warming. So before we show the results, the one neat thing here is that we use some machine learning mechanism to select climate samples so that you can target the extreme weather only in your simulation. Because if you do the 1 kilometer resolution for a large region for 20 years, 40 years, that's very expensive. That's doable, but that's that consume a lot of computational resource and time. So we did this machine learning stuff, and then we were able to actually identify extreme weather pattern, which are mostly either tropical cyclones or so-called monsoon depressions. So like this one on the upper right is a typical tropical cyclone typhoon. So the contours, the blue contours are showing you the pressure. So you can see there is a very low pressure center, But then for the case like this one or this one on the lower left, it's more like monsoon depression because you actually don't have a low center there. But then in our region, you can still get a lot of precipitation due to monsoon depression. So any surprise in the results? Actually, turns out the answer is yes. So as I mentioned, the global climate model predicts the sensitivity to be 60% per degree of warming for exotropics. But then in our simulation, we found that for those extreme precipitation, then the sensitivity can be as high as 16% per K. So the figure is a little bit, I need to explain a little bit. So the horizontal axis is the scale of average. So you get some extreme precipitation, but you can consider, okay, what's the average intensity for a small region of 1 kilometer, or what's the intensity for entire Hong Kong, or for a scale of 50 or 100 kilometer. So the horizontal axis is the scale of your interest. The vertical axis is the time scale. So whether you look at 1 hour precipitation or 24 hour. So the message, interesting message is that if you look at a single point for a short time, like 1 hour, 1 kilometer, the sensitivity is actually, so this is 20% increase, and the temperature increase is about 4 degrees for these simulations. So you can see for short time scale, small spatial scale, the sensitivity is still 6% per degree. So it's consistent with global prediction. But from this high resolution simulation, you can see if you look at a larger scale or longer time, the sensitivity becomes larger. So like the chart on the right is showing you the increase for 1 hour, 12 hour, 24 hour precipitation. Actually, for the same 4 degree warming, you can see the increase is from 25% to 75%. So this is important because actually when we do urban planning or designing, so you are looking at the entire city, and a lot of cities are actually on this scale of 30 kilometer, 50 kilometer. So that means the previous prediction from climate models significantly underestimate the sensitivity of precipitation if you look at the entire city. So what's the reason? So you can see that this figure shows you the decay of the precipitation away from the center of the maximum. So this is average of all those cases. And you can see in the future climate, in the center, actually the change is small, but actually away from the center, the increase becomes larger. So there's more fractional change away from the center. So it seems that this chart is suggesting, okay, maybe there is an expansion of the storm. So the storm becomes larger in the future time. So that's what this suggests. And okay, so then that's the suggestion. But what's the result? Actually, if you look at the data, you will find the opposite answer. Actually, the figure on the left is from a present climate simulation, and the figure on the right is the simulation for the future warmed climate. So what you can see, of course, we can see the increase in intensity of precipitation. So this is millimeter. And then the other thing is actually this center, this eye wall of this typhoon contracted. It becomes smaller. But meanwhile, it also becomes more continuous. So like in this present climate, even in the eye wall, the convections are organized in a few different clusters. But in the future climate, you can see this one, it's a continuous principal rain band. There's not too much discontinuous between them. So the result is that once you have this, if you look at a region like this square box, then because it's continuous, so the rainfall you can get doesn't stop. So if you look at the longer time scale, the sensitivity also becomes higher because of that continuity in the principal rain band. So why is that is the reason? So that's also something we are working on. So the interesting is that, so this set of simulation is from simulation when you have no cloud radiation. So the result is that, okay, if you turn off the cloud radiation, the eye wall becomes smaller, but then there's no change because of warming. So, so it seems that if you actually, the cloud is making the eye wall larger, but in the future climate, their effect becomes somehow weaker. So you see this contraction of the eye wall of the tropical cyclones. So I don't know the physical answer yet, but then let me summarize. So in summary, the current climate model prediction is underestimating the precipitation change for a scale relevant to a city. So at urban scale, the rate of change may be doubled or even tripled if you look at the entire city average precipitation. And that's relevant for flooding, for landslide. Like for landslide, if you look at one single point, even if the precipitation becomes stronger, then that's still one location of a landslide. It may be a bigger one, but it's only one event. But then if you have a future for the entire city, you get quite a dramatic increase in precipitation, then you will get many more events. Actually, the 16% per key degree, the per key sensitivity is for the average. So that means that at the center, the sensitivity is lower, and away from the center, it's even larger than the 16% per key. So in the future, the flooding may actually become more dramatic, more unexpected, and landslide may also be unexpected. Okay, that's all. Thank you very much.
Okay, so thank you very much. That's certainly a very interesting talk, and tell us, we definitely need to prepare our city much better in the event of climate change. Okay, the last talk of this section is Professor Lee, also from the Division of Environment and Sustainability on the sea level rise and storm surge risk.
So good morning, everyone. So thanks for Professor Feng's introduction. So maybe just call me Dr. Lee is more appropriate because I'm RAP in ENVR. So today I'm very happy, very honored to introduce our recent progress in the sea level rise topic and also the storm surge risks. So first, I just gave this flooding picture. When the sea level rises about 1 meter, it's a projection at the end of this century. What do you think? So it seems not a big issue, right? Only very limited regions will be inundated after 1 meter sea level rise. Well, I would say that it's already the worst case, the worst scenario projected by HKO. So if we turn back to see the temperature, actually at the end of this century, even the worst scenario, SSP 5 in CMIP 6, predict like 4 degrees Celsius warmer compared to current climate. If I say that our current mean temperature, global mean temperature is only about 14 degrees. So 14 degrees plus 4 degrees, 18 degrees. What do you think? It's just today's temperature in Hong Kong, right? It's not so warm. Where is the problem? The problem is that no one lives in the average. So if we live in the average of the annual mean temperature, we'll be very happy because every day will be just as warm as spring, not hot, not cold. So when we're talking about the mean value, we first need to consider the fluctuation because mean value will just rule out all of the fluctuations. But for we human beings, we will be just go through all the fluctuations. We have to survive somewhere here. So now we're talking about the extreme fluctuations in the sea level, and also by one of the most severe weather systems just introduced by Professor Shi, typhoon. For example, this is Mengqian coast sea level fluctuation. We call it storm surge. We can see that it caused lots of destructions along the shoreline of Hong Kong. And the right corner is UST, where the roadbed was totally destroyed by the storm surge. So how we measure the storm surge? We have tide stations all around the Hong Kong coast to measure the water level. And if we pick out one station, timing 1, and we just see a relatively short period of the sea level fluctuation, we see something like this, very regular rhythm or melody is actually controlled by tide, determined by the orbital parameters of Sun, Moon, and also our planet Earth. So if we run a tide model, we can nearly perfectly reproduce this kind of fluctuation. Well, this is a calm weather, it's not for the storm surge. So when the very strong typhoon approaching shoreline, it will push the waters accumulated along the coastal regions. And this will cause this kind of upsurge in observation. So if we only run the tide model, we can only reproduce the tide. So you see there is a departure, this is a storm surge. If we hope to reproduce the storm surge, we have to implement very sophisticated numerical models across the atmosphere, sea wave, and also the ocean model together. Because a storm surge actually consists of several components, such as the wave, the surge itself, and also the tide. So at this time, we can reproduce this storm surge. And then I just show that the typhoon Mengqian caused a storm surge. You can see that the spatial plot from the east to the west, the surge level goes up and then dissipate away when the typhoon made the landfall. And we pick out one frame where the eastern Hong Kong confronts the highest surge. And we can see that the model can well capture this process, and the right upper corner is UST. So now we're talking about the future. When we're talking about the future, we are actually more interested in the so-called black swan event, which means that although the probability is low, but once it happens, it will cause very, very huge impact or even catastrophic losses. So we add all the worst scenario to the boundary conditions of our modeling system. I won't go the technical details, but we just try to reproduce the typhoons as strong as Mengqian, Hato, and Vincent with the typhoon signal number 10 raised by HKO. What if these kind of very strong typhoons occurred again in a much warmer climate? So this is a result of Typhoon Mengqian in 2018. If we use a future experiment minus the current experiment, and the left figure is for the wave height, and the right figure is for the storm surge. So the wave height is the transitional water level, and the storm surge, you can treat it as kind of stationary water level. It's below the wave. The wave is kind of topping things on the stationary wave, water level. So the difference, you could see that for the wave is about 1 meter to 2 meters higher if the Mengqian typhoon occurred again in a much warmer climate. Our current wave over the open sea is kind of like 4 meter or 5 meter, right? But we need to take attention because the wave energy is actually proportional to the square of the wave amplitude. So this is about 25 increase in wave height. It will result in more than half of the additional wave energy. And we look at this in another way. We try to bend the zigzag coastline because we more care about the coast issues. And we bend them into axes, and we overlap the storm surges and also the storm waves up. So the blue curves are for the current experiment, and the red curves for the future experiment. You could see that almost along all the coastline, the surge level and the wave level will go up. And in the future experiment, there are actually some very sensitive locations or regions. You can see the river moss will have this spike, and also the offshore islands, because it just confronts the open sea, it will meet the very high waves there. So we see one more experiment, one more case is Hato, 1 year earlier of the Typhoon Mengqian. And you see that actually in the future experiments, the wave height decreased a little bit in the western flank of the open sea. That is because in these experiments, the tracks a little bit shift away, but the storm surge still goes up. And we see that if we just focus on the coastline, the river moss appeared again in the future experiments is quite sensitive to the intensity increase of the typhoon. And this experiment in Vincent is very special. And you see that it's very, very sensitive to the future warming conditions. The wave height increased more than 2 meters over the open sea, and also for the storm surge. Why? Because the Vincent track is so different compared to other two typhoons. It stays almost stationary over the northern China Sea for almost 24 hours. So in the warming experiment, it will extract much more energy from the warming surface to increase its intensity. And if we see the coastal storm surge situation is very different, you can see that surge level for Vincent is not that high, but it caused very, very huge or formidable waves overlapping the surges. And in the future, you can see that almost all the western coast of the Pearl River Delta will suffer so much of the strong waves. So I just gave a concrete diagram over Hangfa Chun that happened in 2018, the Mount Holt case. So if we reproduce or decompose the storm surge level at this moment, we see the disaster, right? The huge waves just overflow the seawall and cause the damages. Actually, from the chart data, we have neap tide only about 1.5 meter, and storm surge 2.3 meter also. If there is no wave, okay, no problem, right? The storm surge still not overflow the seawall, but we have the waves. So the waves overflow and cause the damages. At this time, you can just escape or go higher. So now we're talking about the future. What if the Mount Holt happens again in a much warmer future? First, we need to account the mean sea level rise, 1 meter. And spring tide, tail risk, right? We need to consider the top 1% high tide overlap the mean sea level rise. And catastrophic storm surge is already overflow the seawall. Well, there is still waves. So at this time, you can add all these numbers together, and we can see that only you will be the Superman to escape all this. Okay, this is the final finger. I just add several mean values here. This is 1 meter sea level rise plus 2 meter storm surge plus 2 meter wave height. So if we count the fluctuation of the sea level, and this is the inundation map, do you think is this still okay? Okay, that's all what I have for you. Thank you.
Okay, so thank you very much. So we all need to be Superman in about 30 years' time when the typhoon come. Okay, I would like to invite all the speakers coming out here this morning section, Professor Chai, Professor Shi, and Professor Lee. So just wondering any questions you would like to ask of our three distinguished speakers today, together with Professor Lu. But we'll keep the question for Professor Lu if you have any burning question for Professor Lu. Yes. Yeah. Yeah.
It seems quite quiet, so I will ask the first question.
Okay, please.
I'm very impressed by the inundation map, the last one. I really wonder whether you or the university will recommend to the governments that no developments, residential developments should happen in the northwestern part of the new territories. It is totally red in your map. So would the university take a position and tell the government, please mark it as not for residential development, northwestern part of the new territories. Yeah.
Yeah, thank
but
you.
I'm worried that people would buy residential flats and then they will be stuck at the middle of the sea. So.
Yeah,
whoever going to buy the flat in Northeast will be a Superman.
Yeah, thanks for your very good question. Yeah, if we consider the very extreme scenario, right, the inundation map will be really catastrophic. So that's why we think it's actually we need to action now to build up our infrastructure like the seawalls, wave breakers along the coast of the vulnerable regions in Hong Kong. So that's my thinking on this. Yeah, thank you.
We definitely need to pass. Well, because as it pointed out in the today's presentation and some of the point we will write to the government. So definitely we will take this one into account. Yeah, peace.
Hello, I have a question for Professor Jia. Thank you for your presentation on the sponge city construction in China. So I was wondering, because I've heard of many other similar programs from other countries. For example, Australia, as early as maybe 1980s, they already started water-sensitive urban design. And in the US and Canada, I think they started the idea of low-impact development. So I was wondering what is unique about the sponge city in China and how is it similar to but also different from the other programs? Thank you.
Okay, thank you for your questions. Yes, Sponge City, we just said we learn from international countries. They have some similar term. But I think different countries, they have different developed stage. Also, they have a different natural condition. So maybe the focus is different. For example, in United States, this is low impact development. So usually they only focus on the source control facility. Maybe they have a manure drainage system, green infrastructure. Traditionally, they have a relative good, already good infrastructure for traditional. So they only focus on the source control part. For Australia, maybe I think the Sponge City is similar, most similar with sensitive urban design in Australia. All they consider the city as a whole, not only part of the city. So, but in Australia, most the local water, shortage of water, so they maybe more focus on the how to harvest the water, how to utilize the water. In China, we have large areas, different parts, north, west, west, east, dry, wet, different place. And China is still the developing country, so the drainage system is not good enough. So we still have the problem on the traditional grease pipe system. So so in this case, China first learn from the other countries similar term. We also have our Asian philosophy because in China we have a lot of Asian heritage for how to deal with the stormwater. We have the case study in Beijing Tuancheng or in the Anhui Hongcun. Also we have different, they have recognized world heritage. So they have the wisdom to deal with the stormwater in the Asian China. So I think the Sponge City, we first learn from other countries. Also, we just continue with learn from our Asian China's wisdom. But I think the difference is China's Sponge City, we just think of the city as a whole. all we need to consider the source part control, process control, also the receiving water together. So that's also the different agency, they will working together, different experts, they will working together. So not only part of that, it's a whole city, I think, is the main difference.
So the central government are much more coordinated
yes.
in terms of sponge city construction. So,
yes. Yeah.
Please.
Hi, this is my name is M.K. Leung. I'm an architect. I have an interesting observation this morning and 2 questions. The first observation is, seems like if we want to build and for sustainable development in Hong Kong, we seem to have a very interesting challenge. If we build inland, we will be too close to the debris flow. If we build close to the coast, and we have the problem of being a Superman. So then my 2 questions is, first is to Professor Chia. And I fully concur with the interesting challenge that we are heavily urbanized. And especially, for example, like Hong Kong, we have a very compact city, which we don't have too much horizontal ground for ground infiltrations. Then, while looking at the BMP, which we probably on hand, seems like it's focused on horizontal ground infiltrations. And well, how we may think of more BMP for a vertical city where, well, there are not much horizontal ground. This is my first question. My second question is, again, about Superman. Is, well, if we look at the city 2-dimension, seems like there are quite a number of red areas we need to be aware. But if we think of the city as a vertical system, then probably we may design our buildings and infrastructure in a different way from a 3-dimensional configurations. Meaning, well, how would you envisage from your studies the lower floors of building should be designed, rather than no building zone, how the buildings should be designed for the first 3 to 5 stories?
Okay, maybe Professor Chai first.
Okay,
horizontal sponge city.
Okay, thank you for your questions. Yes, actually, in urban areas, land is very valuable. So usually the government want to sell the land for construction, not for the natural. So I think usually for the sponge city, or for the city like Hong Kong, we have a very tight land. And for the source control, we call BMP or LID, different things. So the faction, we just want to this kind of natural land because they have multi-benefit, not only for the flooding, but also for landscaping. So I think for a good city, they need to have a certain natural land, and we can put this natural land play their roles or enhance their function for the stormwater management. In the vertical, usually we see the green roof or the green wall, they can be used in the city areas. But this, when in China, for some buildings, some for government, for some school, they use this kind of techniques, the green roof. But in the dormitory and community, there's still difficult for a lot of reasons. So in China Sponge City, we do not to rely only for the green infrastructure that cannot deal with all the extremely for the big storm. So we just in our research group we consider how to combine the green source control green infrastructure, also the green infrastructure and the receiving water body together. So just make them to play their roles and how to, in some extent, to enhance their roles. So I think this is the scheme we can consider for different cities based on their natural and social conditions, not single optimized scheme for all the city. Thank you.
You know, Hong Kong is normally build a lot of underground tank.
Yes. So this kind of tank is we call the green infrastructure. That is also very useful. So in China's smart city, we also think about that, use a tank, storage tank to do this. So storage tank is good for, before the storm, we can use that, and after it's for utilization, how to use the storm. That's also a good method to do. Okay. But the maintenance is a problem. Thank you.
Okay, the second question about
Superman,
and the first 3 floors. I had a discussion with Professor Lam yesterday exactly about this one, but I let Professor Lee answer this question.
Okay, thanks for your very good question. First, I have to admit, really, I have very limited knowledge about architecture, but I need to clarify several things. First is the inundation map, but just plus the mean value of the storm surge and also the wave. Just as what we mentioned, the mean will rule out all the fluctuations. Actually, it's highly different regional heterogeneous. For example, in the quite inner regions, the outlying islands will just block the very high waves. So the waves will drop, the wave energy will drop significantly, especially we call the very good Victoria Harbour. Actually, within the Victoria Harbour, the wave height can be lower very much compared to the eastern Hong Kong islands. So that's one issue. And the other is that talking about how we design the lower floors of our buildings. If we build our buildings near the vulnerable coast, I think it's important for us to give more protection along the coast, such as the seawall, higher seawall. Also, in the open ocean, if it comes from the open ocean, I think it's important to build kind of wave breakers or something. Also, I think yesterday, some expert mentioned about the buffer zone. We can build such as dozens of meters of buffer zone along the coast. It can also be very good for taking walk or something because it's basically covered by vegetations and kind of landscapes. So this will protect the relatively inner buildings. But also for the lower floors of the building, I think we still need some kind of protection, but I really have limited knowledge about this, how we do it better. So that's my understanding on this question. Okay, thank you. Thank you very much.
Thank you. Yes, Shui. Yeah. Okay. Why don't and then yeah.
Oh, thank you. I have a question for Xiaoming. I like you this work about the fractional change of extreme precipitation, like under warming conditions. So you mentioned like at a larger scale, like 30, 50, or even 100 kilometer scale, the fractional increase is actually higher than the smallest scale. So I think one of the reasons could be under the warming condition, the fractional change of precipitation actually will be experienced by more areas. So the storm itself
Like if we measure typhoon by like wind, the storm size, the size of the storm may not change. You actually show the decrease, but the area actually experience extreme precipitation, like very high rain rate, could be larger because of the warming. So I think that actually is kind of consistent with the other studies, like this fractional area experiencing extreme precipitation will be a lot wider in the warming conditions.
Yeah. Yeah, thank you. Yeah, thank you for your comments. Yeah, yeah, it's true that there are also other studies who found similar things. Like I think there are simulations for convective system in North America, and they also find that the volume of rainfall they get will increase, not just the intensity at the center.
Okay, we have a couple more questions before we have the break.
Okay,
yes,
thank
please.
you, Professor. I have two questions. The first one is for Professor Jia from Hong Kong, Tsinghua University. So if we use sponge cities concept, the output should be much cleaner than the approach, traditional approach. But my question is, if every cleaning process just underground, is it really good for vegetations and also agriculture? Yeah, this is my first question. And the second question is for Professor Shi from Hong Kong USD. The question is very simple. So is it possible to forecast the duration of extreme precipitation? The duration. Yeah, thank you,
yes,
Professor.
Please.
Okay, thank you. I just want to confirm. So your question is about the spontaneity concept on the vegetation. Is there always good for vegetation? Is that right? Is your questions? Okay, thank you. So currently there have several research about how to select the suitable vegetation localized. Also, they have the function, for example, can deal with the wet or drier. Also, if they have the certain pollutant, this kind of vegetation can live there, also can purify the pollutants. In our university, we have a school of architecture, several professors in the school of architecture to do this kind of research. So before, we have different government agencies, they in charge different things. So when the central government promote the smart city, especially the agency for landscaping in Beijing, they disagree to discharge the stormwater to the wetland, to the grass. This is the runoff is too polluted. They will be harm to the vegetation. So they disagree that. So even though they said certain runoff, for example, from the highway, they do not agree to do that. But along with the time, they also have some. We think the smart city concept is good. It's a right thing, but we still need to select the suitable vegetation. They can live in the certain conditions. So this is a problem.
Thank you. Professor Xu?
Thank you for your question. Yeah, the short answer is yes. So all those analyses are based on computer simulations, like what Zhenning did. So you have data for like have a few days of simulation for each event, and then we can actually do detailed analysis about how its temporal behavior.
Yeah, the duration. Yes, maybe the last question of this section. Yeah, please.
Okay, thank you very much. This is George Liu from Purdue. I have two questions. One is for Professor Li and one Professor Shi. Okay, Professor Li did an assumption that the 1 meter sea level rise. Okay, as far as I know, usually currently the rate is about 3 millimeters per year, right? So 1 meter scenario will be 300 years later. And I watched I looked at the website, the Hong Kong, the woman's birth rate is about 1.4 children per woman. Okay, so it's much lower than the yeah, the normal, okay, expected birth rate is 2.1 per woman, okay. So after 300 years, okay, the how many population in Hong Kong is hard to say, okay. This is the comment, okay. The question to Professor Shi, if I'm right, okay, your simulation is after the 80 years later, okay, so the size of the tropical cyclone is getting smaller. I'm right? If I'm answering.
So it's just the inner core, the eye wall region seems to be becoming smaller.
Okay.
I haven't done analysis for the entire, for other standards of the size.
Okay, just recently we did some data analysis of for the North Pacific, North and the South Pacific Ocean. We for the 367 tropic cyclones during 2008 and to 2020. And we found that we used the altimetry satellite data to get the water vapor observations, and we found that okay, we estimated the radiance of the water vapor around the tropical cyclone actually is increasing in both North and the South. Both North and South Pacific Ocean. Every year it's about 4 to 4.7 kilometer, the band of the water vapor. So we think okay, the impact of water vapor, the tropical cyclone is increase.
Yeah, maybe. Yeah, I was also thinking about it. So I haven't finished this study yet.
Okay.
And it's true that there are different ways to define the size of a tropical cyclone, and sometimes they don't have the same response in terms of increasing or decreasing. So I think we should talk more and maybe.
Yes, I think you two can talk more. Okay, okay. I think I better stop here because I do not want to delay the too much. If any of the audience here would like to, find out a little bit more, you can certainly individually contact our distinguished speaker today. Okay, I would like to take a short break here. In the second section, we have 1, 2, 3, 4, 5, 6. We have 6 speakers. Okay, so we will try to give each speaker no more than 15 minutes. Okay, so as I mentioned earlier, so the second section of the topic is forestry, heat stress, and infrastructure. Okay, the first speaker is Professor Billy Hao from School of Biological Science, Hong Kong U. Thank you.
Good morning. Thank you, Alexis and Jimmy, for inviting me to share my work with you. So I'm going to talk about forest and its role in climate mitigation, adaptation, and resilience. First of all, when I prepared this presentation, I thought there were very little biologists here, and there will be little understanding on biodiversity and ecosystem services. So I prepared quite a few slides at the beginning just to set the scenes for the talk. I hope you bear with me because from the program and from talking to various people, you seem to know a lot about nature-based solution and ecology. So biodiversity is in crisis. I'm sure you know IPCC, but I guess many of you may not know there is also an intergovernmental panel on biodiversity and ecosystem services. They produced a report in 2019, which is the most comprehensive assessment of biodiversity and ecosystem services in the world. Of course, the result is depressing. So there are unprecedented and dangerous decline of biodiversity and ecosystem services. And the report pointed out that around 1 million species are threatened with extinction. To put this 1 million into context, the total number of described species is only around 1.2 million. So this is actually a huge proportion of species being threatened. And the species extinction rates are accelerating, especially in the last few decades. But the report also churned out some hope, saying that we need to have collaborative responses to change this decline. We need to work together, especially with those with vested interests, and try to use the public good, the overall benefits of the mankind, to try to force those with vested interests to change. And right now, there is a COP meeting for the Convention on Biological Diversity in Canada. And one of the targets is to convince everyone in the world, every country, to list at least 30% of their lands and seas as protected area by the year 2030. Now, in this aspect, Hong Kong is in a good position because for land, we already have 40% designated under control park. But for ocean, we are far below 10%. So there are still a lot of work if Hong Kong is going to catch up with these. But yet, whether the countries will agree on this target, we don't know. We have to wait until the end of the meeting on the 19th. So things are still going on. So why is it essential to protect biodiversity? And we know all human activities are changing the environment, both the physical environment and the biological environment. By changing the species richness, evenness, and composition, we are affecting ecosystem services and processes. I'm sure you all heard of all these terms before. And the Millennium Ecosystem Assessment actually put forward these linkages between the ecosystem services, like supporting, provisioning, regulating, and cultural services, with all the 5 key important elements that sustain the well-being of mankind. I mean, you can refer back to the assessment for all these different results. And because of these, there is urgent need to protect biodiversity. And IUCN, the International Union for the Conservation of Nature, together with World Bank, put out in 2016 the nature-based solution concept. And it's been picking up rapidly, especially in Europe. And some speakers are also talking about this in the morning. So these are the 7 societal challenges to sustainability that the nature-based solution identified. So by developing these solutions, we hope to achieve sustainable development, especially under climate change. And nature-based solution is far more than just climate mitigation. It involves actually protecting all the biodiversity in the world. And nature-based solution could be developed based on natural ecosystem by managing them, using them, or we can also restore degraded ecosystem. And the other extreme is we can create new system to generate nature-based solutions. Just to give you some idea, nature-based solution can also be used with other types of interventions. It's like this case when we have agroforestry as a nature-based solution to solve the food security issues. There are other social systems like the fair trade, food market price system, which should work together with the nature-based solution to achieve sustainable development. And this is a very simple illustration of how nature-based solutions can be developed. This is the original landscape, a coastal area with village, forest, and so on. And in the courses of human activities, all the mangroves were removed. More high-density residential areas move in. Many forests, you can see, were thinted. And therefore, it generates flooding problems, storm surges, as discussed in the first section. And for nature-based solution, it means we need to restore the coastal mangroves to reduce the impact of storm surges. And we need to restore the forests to secure the water cycle. Together with infrastructure like a dam here, we can control flooding. So this is just a very simple illustration of how nature-based solution can work. For coming back to forest, which is the focus of my talk, is forest can actually address all 7 societal challenges without doubt. And there are a lot of scientific evidence supporting this. Come back to Hong Kong. Hong Kong was originally 100% covered in forest more than 1,000 years ago. And in the courses of the last 1,000 years, because of farming, human activities, development, cutting, burning, our forest is now reduced to around 24%, according to the latest survey result published early this year, using remote sensing methods. So we have around 36% of degraded vegetations that are grassland and shrubland. They were formed after cutting and burning of hillside forest. And we only have about 29% of tree covers as natural forests as well as artificial plantations. Note that these are all secondary forests. That means they're not original. They were formed after disturbance. And the total developed area in Hong Kong covered in concrete is only about 25%. So these percentages are important. Look at Hong Kong's climate action plan. Again, I'm sure most of you are very familiar with these. And you look at the strategies Hong Kong is focusing on. For example, green electricity generation, net zero generations, green buildings to save energy, green transport to reduce carbon emission using e-vehicles, waste management and reduction. These are the 4 strategies. And if you look at the action plan, there was no sort of mentioning of nature-based solution. It does mention a little bit, say, nature can provide mitigation or adaptation, but there were no quantitative assessment whatsoever. So is the forest in Hong Kong not important? Now, we still have 30% of forest and another 36% which potentially can turn into forest. How important they are? So look at Hong Kong. Hong Kong's landscape is very unique in comparison with many other cities because we are inscribed in a green landscape. Cities is developed around both sides of Victoria Harbour, new towns in Zhenning, Sha Tin, Tai Po, Tsuen Wan, and so on. And the benefits of hillside forest, example, cooling effect, could easily be felt even in urban areas. So the city structure and geography of Hong Kong is very conducive to biodiversity, recolonizing even the urban areas. So how much carbon is stored in Hong Kong's forest? Now, I did ask senior government officials, including the current Secretary for Environment and Ecology, why nature-based solutions not included in the climate action plan in Hong Kong. One answer, it was there was not much information about the ecosystem services and also, for example, carbon storage in Hong Kong. So according to the FAO, these were the proportion of the distribution of carbon in forests. Above ground biomass means all the trees, leaves, and so on. And also in soil, the ratio is roughly 1:1. And this was based on an estimation based on the research done in Hong Kong and many other forest geoplots. Now, this is a global program of large size forest plot, 20 hectare to 50 hectare. Within each plot, all the trees were surveyed, geolocation marked, and there were reserved requirements in the plot as well. And Hong Kong had a plot which we set up in Tai Po Kau Forest, 20 hectare. So all 81,000 trees were marked and surveyed. And based on this figure, we calculate that in Hong Kong's natural forest, by the way, Tai Po Kau is a secondary forest, the average carbon storage, you're talking about 142 tons per hectare. This is calculated based on this equation here, which use primarily the diameter at breast height, which is the tree trunk, also the wood density. Now, there are incomplete data on wood density. So in this paper, we use species if the wood density is available. If not, we try to use the genus. Even if that is not possible, we go to the family. So there are errors in it. And there is also an E here, which is about the environmental factor. Now, this is used because we don't have good enough data set on the ground to do a more accurate estimations. On the other hand, there is also a paper talking about soil organic carbon in Hong Kong. You note, in secondary forest, they're talking about 146 tons per hectare, which is roughly 1:1, in line with the FAO predictions of the distribution of carbon. So with this vegetation structure of different type, can we come up with a more accurate estimation of the carbon stored in Hong Kong? So based on these figures, I calculate that the existing stock is roughly around 48 million tons of the forest. And this excludes grass and shrubland because of no data. If I plant trees, convert all the shrubland and grassland into forest, we will gain an additional 7 million tons of carbon. And I estimate we can do that in around 15 years if we start now. And put this into context, according to government's target, if we generate 7 million tons, we're talking about 2 to 3 million people's emission in 2035. But this is, note, this is standing stock. This is not about annual increment. We don't have information on annual increment. So is accuracy important? Is this formula used in pan-tropical area good? The answer is not. There's a better formula developed by a group of scientists by actually harvesting the tree. It was an amazing job. They harvest a lot of trees, weight it, and then calculate the model. So it only depends on three factors here: diameter, height, and also the wood density. So if we have ground data of all these 3 parameters, we can actually accurately measure carbon stored in forest. So I'm doing this at the moment. I'm trying to sample 70 plots in different vegetation types in Hong Kong. I will measure all the trees, including mapping them, diameter, height, and I'm also collecting wood density. Now, I also do LiDAR measurement here, which I will talk about this in a minute. And I hope to come up with an accurate assessment, a better model for Hong Kong, which is also applicable to Guangdong and Taiwan. And for wood density, I'm actually building up the database. There are 400 tree species in Hong Kong. And I will sort those species with data from the global database. And I would identify dominant tree species because I guess I do not have the ability to sample all 400 species in Hong Kong. So I have to prioritize. And I will collect species-specific wood density. As you can see, I have to drill into the tree, take a sample out, and use it to measure the wood density. So I would try to do it from trees that are going to be felled because this method may damage the tree. So if I collect sample from tree to be cut, I feel less guilty. Then I would try to collect sample from trees fallen during adverse weather. And also, lastly, if there are essential species that I need, I may have to collect it from live samples. But I put it as the last strategy. For LiDAR, this is the usual method people use, remote sensing method. Most people in the world use this method to assess carbon. But there are problems. There are segmentation problems, there are errors, and this study was conducted in Europe, trying to compare ground data versus LiDAR data in estimating forest carbon. And there were errors, both in estimating counting the tree. Small stems are missed, mostly, and large stem better. But in segmentations, estimating the DBH, there will be overestimation for small stems, but underestimation for large stems using LiDAR methods. And the overall result is there is an underestimation of the carbon storage in forests if we use remote sensing method. And remind that this study was done in temperate zone. So the forest is more simple, more uniform, less diverse. And the area will likely be larger in the tropics because we have more complicated forest. So we will need ground data to verify all the method we're trying to do. And I hope with these, we are able to quantify the forest carbon better and use it as a meaningful nature-based solution for Hong Kong and also for the region. So that's what we're doing now. Thank you.
Okay, so yeah, thanks, Billy. Okay, so this is the second talk. I would like to introduce Professor Yin from the Civil and Environmental Engineering here, HKUST. Her title is in Hot and Dry Extreme under different emission scenarios.
Okay, thank you. Good morning. I'm Eun-soon from HKUST, and I'm very happy to share my recent study in front of relevant research community. Today, I'm going to talk about hot and dry extremes expected from different levels of global warming. We have already observed unusually hot extreme event, and temperature records are being continually broken worldwide, and China is not an exception. And we repeatedly heard about it yesterday, and even you saw the same figure as well. And I'm in addition to hot temperature, I'm also interested in dry extremes. We tend to overlook drought risk in monsoon region, but actually that is not really the case under warmer climate. Then, of course, the synergetic impact of compound hot and dry extremes will be way more destructive compared to the single event. So, seemingly, we will experience more and more unbearable summer in the future. And indeed, latest IPCC report clearly addresses the compound hot and dry extremes will increase in nearly all land areas. But this description is too generic. The thing is how severely the global warming will exacerbate regional to local scale extremes beyond our adaptation. So we need to investigate a region-specific emerging pattern using a customized data set. I will do that. And then more importantly, if global warming is really attributed to the human-induced greenhouse gas emission, then what is the tangible benefit from the climate change mitigation? We need to find such a clear mitigation benefit that we can really reflect the emission cut to our policy. And these questions we can able to answer with the aid of the climate model simulations. Now I play short animation to visualize how temperature is likely to change in response to different emission scenarios, so-called SSP2 and SSP5. Climate model can produce physically based long-term climate information by very far future, like at the end of the 21st century, in response to future emission scenarios. As shown in this figure, we can assume several social-economic pathways under different the plausible narratives of what might happen in our future society. For example, if our society put the most priority on sustainability, then we try to aggressively cut down our emissions like SSP1. But if we keep delaying emission reduction, then opposite situation might happen like SSP5. And by comparison of these two patterns, we can clearly see a strong relationship between CO2 concentration and temperature increase. It's safe to say the degree of warming totally depends on our future emission pathway. The effect of temperature increase does not limit to the extreme heat event. Warmer temperature can critically affect atmospheric moisture demand and surface dryness through evapotranspiration. For example, many climate models, more than 80% of many climate models project an increase in precipitation over China under global warming. But in spite of having more precipitation, surface soil moisture, which is a direct indicator to measure agricultural drought, is likely to decrease across southeastern China, and it's mainly due to enhanced the evapotranspiration. So with a continuously warming condition, temperature will sustain in its effect in intensifying both hot and dry extremes simultaneously. All these patterns from the global model simulation from CMIP6 dataset. And they provide such a big picture, but they are not sufficient for understanding a particular place's emerging patterns. It's because current state-of-the-art global climate models mostly adapt their resolution around 100 to 200 kilometers, which means just 1 or 2 grid boxes represent the entire Hong Kong territory. But if we zoom in surrounding region, the actual geographical features are very complicated. So to overcome this limitation, regional climate model can be nested within global climate model over some specific area without tremendous computational cost. This is one way we can get very fine scale detailed climate information. However, regional climate model is not a magic box. There are some issues to be tackled when using regional climate model. First, the regional climate model's performance is very dependent on the global model's performance used as boundary condition. In addition, it may not be possible to obtain as many ensemble members as we usually do from global climate model. So it's very important to select optimal global climate model for dynamical downscaling. In general, we consider 2 criteria. First thing is model performance during the historical period, and second thing is warming sensitivity at the end of the 21st century. Back to this figure, we can see very diverse warming sensitivity from the global model simulation. Different models produce different level of global warming in response to the same emission scenario. For example, of SSP5, the model with lower warming sensitivity even shows the less warming compared to other models forced by lower emission scenario SSP3. So which one should I downscale? This is one issue. And finding the best model performance is very challenging because all climate models have their own strength and weakness. So to overcome this issue, we downscaling bias-corrected global projections, but with the multi-model ensemble warming trend rather than having a particular model's warming trend. For this, we developed WRF double-nested modeling system, and we customize its performance over southern China region. Here, before presenting the future change pattern, I may need to demonstrate the added value of high-resolution simulation during the historical period based on the comparison with the observation. Otherwise, it's very difficult to justify why we need to carry out the dynamical downscaling in spite of it's very expensive. This slide shows some distribution of daily precipitation and temperature at 2 locations. Global simulations here, blue color, shows very strong dry and cold bias at both the regions. And more importantly, the global climate model completely failed to capture such an extreme event. So this is a very critical limitation to understand the future extremes. On the other hand, downscaling result from WRF shows very good improvement, and the distribution shape and tail bound shows very similar pattern with the observation. Now I move to compare the future temperature change in southeastern China projected from global and regional climate models. For better comparison, global model simulation are only displayed over the regional model domain. Then it's very clear downscaled result shows much greater regional details compared to the global model. And under SSP5 scenario, southeastern China is likely to experience a substantial warming with a strong regional variation. So our question is how this kind of different level of warming can be actually translated into the probability of our future compound hot and dry extremes. So finally, this slide shows the joint return period of hot and dry extremes. For hot extreme, I pick highest maximum temperature on a yearly basis. And for assessing the future drought condition, I calculate Palmer Drought Severity Index. This is just one index to represent temperature, precipitation, and evapotranspiration change. And larger negative value indicate severe drought condition. First, at the Hong Kong observatory site, this black dot indicates individual years extreme event, combined hot and dry. And this the solid circle indicates 90% of possibility. So, and this black the star indicates the median value. For the extreme event, I also select one, the yellow star that corresponds to the upper 5% possibility. So if we focus on this red star, over the 36 degrees Celsius of the maximum temperature and PDSI is -4, then return period under the current climate around 80 years, like something like that. But even the exactly same event, but under SSP2 scenario and SSP5 scenario, then their return period is sharply decreased, which means from a statistical point of view, such an extreme event we may experience once per lifespan in the current climate will appear every 8 years or every 3 years in the future according to the warming condition. Now I add the distribution of the historical simulation. We can see some discrepancy against the observation, but this is model result, so we should not expect the perfect match. And if we focus on the median value, we can still think the model simulation shows very reasonable performance. And here I added the SSP2 and SSP5 simulation. Then it's very clear under the global warming, the distribution shape is totally changed and they move to the right upper direction. It means in the future, the dry and hot extremes will increase at the same time, simultaneously. So let me summarize my talk. Based on today's talk, I want to give you impression dynamical downscaling is helpful to produce the fine-scale, localized climate information. And by comparison, SSP2 and SSP5 projections, we clearly see some positive benefit of climate change in mitigation. And such a scientific information is very important for the developing some future policy. And last one, I would like to emphasize climate data uses. These days, unprecedented level of climate data are available, and even non-climate experts can easily assess many different types of climate data sets. But without correct understanding, you just apply your research, then it's a little bit problematic. So, and is particularly CMIP6 data, dynamically downscaled CMIP6 data is still very rare. So but I'm very happy to share such a data if you want to apply your research. So if you are interested in assessing this data, please contact me. I'm really happy to share such a data with you. Okay, thank you.
Okay, so thank you very much. Talking about all these extremes, and you know, as the previous two speakers mentioned, all these extremes will happen more often. And certainly they will be affecting every one of us. Of course, it will be affecting more vulnerable groups. So in the next two talks, we will talk about how we're protecting all these vulnerable groups. So our next distinguished speaker is Professor Laurence DELINA, and he's also from the Division of Environment and Sustainability here. The title of his talk is on overheating and energy insecurity in Hong Kong's vulnerable populations.
Thank you, Jimmy. Okay, very good morning, everyone. I know it's cold today, but as Professor Im had mentioned, it will be really, really hot in the coming years and decades, especially in the summer. Okay, so I'll be talking about overheating and energy insecurity in Hong Kong's vulnerable populations. And thanks to Alexis, for kindly inviting me to present our project, which has recently started. We just started actually in September this year, and we are about to collect data in the summer to make sure that we get the most systematic and scientific data. All right, so why study urban overheating? We know this already, and we keep on talking about this morning. Just a few minutes back, Professor Im had talked about that we will anticipating hotter nights and very hot days, and even cold days for Hong Kong, especially in the summer, hotter nights, hotter days in the summer. But yesterday, Dr. Cheng, the director of Hong Kong Observatory, makes this really terrifying. I'm very, very terrified. Hong Kong will be very, very hot in the coming years. And with urban heating, the most dangerous thing that can happen is that it will cascade with other vulnerabilities. So my research group are very interested in looking at urban overheating in Hong Kong, not as a single phenomenon, but as it cascades with other vulnerabilities. Hong Kong will experience urban overheating due to combined effects of heat waves, hot days, and also urban heat island effects. So UHI plus hot days, hot nights, combining together to form this new vulnerability. But again, we are interested in cascading extremes, so the emergence of parallel risks, hotter days, hotter nights, and if we have future pandemics, so there will be again lockdown scenarios, economic downturns, and of course the extant vulnerabilities that individuals and households have been already experiencing. And this cascading extremes can lead to serious environmental, social, economic, and health consequences. So you cannot really look at it as a single phenomenon. So it is very, it's embedded in our extant vulnerabilities. And when we say about embedded vulnerabilities, it also impacts different aspects. So not only about energy use, because we will be using more air conditioning system, but also water use, and there will be impacts with regards to outdoor and indoor thermal comfort reduction, of course, the possibility of increasing deaths. So energy demand, especially for cooling, will continue to increase as we experience more frequent extreme heating events. And again, already vulnerable persons or people and households and social groups, which are the point of interest in my research group, are at risk of being energy insecure in their homes or at the places where they work. So this is the essence of the problem where my research group, are currently working on. So this is a social science perspective of the natural emerging phenomena that Professor Im had mentioned and the Hong Kong Observatory had mentioned yesterday. Why vulnerabilities for vulnerable populations in Hong Kong? Largely because this perturbation, this new vulnerability can further result in social and economic inequalities in the city. And extreme heat could result in excessive health burdens to this extent vulnerable groups. So my project is being funded by the Hong Kong Research Grants Council, and it extends my group's work on hazards and risks to and resilience of vulnerable groups. So we're very interested in looking at vulnerabilities in these groups. For instance, I have an ongoing project that looks at climate fragility risks in the Philippine Bangsamoro, funded by the United States Institute of Peace. So we are almost done with that. And an ongoing project on resilient rice farming in indigenous landscapes of Jatiluwi in Bali in Indonesia and in Ifugao in northern Philippines, also supported by the Hong Kong Research Grants Council. Our project is very different because it's a social science policy focused kind of project on the impacts of urban overheating. And again, as it embeds with extant vulnerabilities. So we are trying to fill in a crucial gap, which is basically the missing social science analysis of this emergent vulnerability in Hong Kong, especially as it impacts the city's most vulnerable populations. So we hope to expand our understanding of the physiological and the psychological impacts of urban overheating, especially on the concept of energy insecurity when people need a lot of energy to cool themselves, and the awareness of these mitigation strategies in our city. So it's very important to note here, and really want to underline, that this is not a medical study. We're looking at people's lived experiences and well-being. So let me just briefly describe or define what energy insecurity is. So this is a concept that can be defined as the lack of access to and the unaffordability of safe and sustainable energy. And it occurs across several forms of energy services, not only for lighting, but also for cooking and also for cooling, as well as for technological, medical, and other life-sustaining devices. So we are interested again in responding to these particular gaps. So there is, at the moment, no recognition in Hong Kong policy documents on the concept of energy insecurity and energy poverty in its official statistics and energy policy. So the cost of electricity in our city is not that expensive. So that's why I think the HKUST really doesn't pay attention on the concept of energy insecurity. Little is also known about who these vulnerable populations in Hong Kong to energy insecurity, who are the city's energy poor, where they are located, the intersection of their vulnerabilities, extant vulnerabilities with energy insecurity, the overlapping impacts of this particular deprivation on their well-being as well as on their dignity, and how they cope with this existing and emerging vulnerabilities. So in this project, we are looking to respond to 5 research questions. So understanding who the actors are, who the energy poor are, who are the energy insecure populations in Hong Kong, where they are located, and how this energy insecurity intersects with their extant other vulnerabilities, how they cope with energy insecurity, and what should be done. So while we are looking at, we're looking at what are they experiencing, we're also producing impactful work for policy and programs. So we are using multiple methodologies to respond to this question. So we have public opinion surveys, interviews, observations, and desk reviews. So as I've mentioned, we just had started, but in January, which is just next year, in a few weeks, we will be deploying our public opinion survey with the Hong Kong Public Opinion Research Institute. In the winter and the summer of next year, we'll be conducting interviews, which include story completion as well as participant observation. We are currently conducting desk review of the extant literature, basically secondary data on these topics. So we'll be analyzing our data, hopefully in the fall of 2023, when we are done with data collection, using this analytical framework of energy justice, which is a concept in energy research and social science. So energy justice is basically a concept which mentions that all individuals should have access to energy that is affordable, safe, sustainable, and able to sustain a decent lifestyle. So energy justice have 4 key tenets. So distributional justice, so everyone should share as much as possible equally with the cost and the benefits of energy systems. Procedural, everyone should have an opportunity to participate in decision making. Recognitional justice is about recognition of who actually were impaired, whose well-being are impaired by energy systems. Restorative justice is how to address those different types of injustices. So there are different aspects of energy justice as well as you can see in the screen. So this is basically the relationships between our research questions, our 5 research questions, and the analytical framework that we are using. So the project takes a multidimensional and intersectional framework to analyze Hong Kong's energy insecurity. So as I've mentioned, we really would like to produce impactful policy suggestions and recommendations from this project to provide inputs into future decision and policy making aimed at closing this particular insecurity. So our members, the team is comprised of myself, Professor Tam from HKUST, Professor Ma from Hong Kong Baptist, and we have collaborators from the UK, Professor Castanbroto from Sheffield, Dr. Jenkins from University of Edinburgh, and my MPhil student, Ms. Chloe Chen. So for our interim findings, we just very briefly, we have conducted some desk review of the secondary literature, and we have looked at about 44 44 studies at the moment, and we have initially identified the following hotspots based on our spatio-temporal assessment, considering the heat risk and other vulnerabilities. As you can see, Kowloon City, Kwangtung, Shamshoipo, Wanchai, Mate are the hotspots in the city. The vulnerabilities are in terms of AIDS, social isolation, those living in low-quality housing, lower educational level, and language barriers. So there is some evidence about who constitutes energy insecure populations in the city, as you can see from this slide. And there are also some sectors in society with insufficient evidence. And we try to fill in these gaps as we move along in our project. The studies about the probability of a household suffering from heat-related impacts. Thus far, we found one of the 17 studies using qualitative and use interview methods, and we would like to actually expand on that because our work is largely social science and qualitative work. So 6 of those 16 quantitative studies collected new data and 10 used available ones. So our NTRM findings are as follows. There is insufficient household level analysis to verify those who consider themselves energy insecure, whether they indeed experience energy insecurity. There's also insufficient research on households' coping mechanisms, how they approach this new form of vulnerability. And there's insufficient research on whether households have the means to afford air cooling services. So as I've mentioned, we are still continuing, and we really hope to produce something important and impactful work for the people of Hong Kong and the HKUST. So Ms. Chloe Chen is in the audience. She is actually working with me since September, and we have produced a lot of good work, I reckon. So we are ready to field out and deploy our instruments in the next year. So if you have questions, please reach out to me or to Chloe. Thank you very much.
Okay, thank you, Professor DELINA. That's definitely a very important piece of work to identify the vulnerable groups in Hong Kong and seek help, and every one of us can do something. Okay, let us move on. Professor Liu from the Jockey Club School of Public Health, CUHK, and his title is Temperature, Air Quality and Health, Implication for Future Climate. Please.
Thank you, Professor Fong. First of all, I would like to thank Professor Lau and Professor Fong for organizing this conference and invite me to give a presentation. So today I'm going to share some of my research findings and discuss a little bit about climate change and air pollution and public health. So this is the content I'm going to discuss today. Right? So we know that climate change impacts every aspect of the world we live in. So certainly public health is an important part related to climate change. And climate change can have a direct impact on public health. Right? I will give you a couple examples how temperature extreme can affect occurrence of chronic disease. And I will also give an example how temperature can affect the infectious disease. And climate, in addition to direct impact, climate change can also have indirect impact. That means the climate change can affect our environment, and then the environment affect our health, right? So I will use weather and air pollution as an example. And finally, I'll discuss a little bit about the research implication. So we have 2 studies about the direct impact of temperature extremes on chronic disease. The first study is about the health effect, right? The health effect of the cold spell. The health effect of the cold spell. So this is a quite old study. So in Guangdong province in 2008, actually there is a very severe cold spell, right? So we select 3 cities. One is Guangzhou, one is Nanxiong, and one is Taishan. So you can see that during this period, right? So the temperature in these 3 cities actually is quite low, right? It's quite low, less than 6.3 for Guangzhou, and it lasts around 18 to 20 days. So this actually is a quite severe cold spell because we know that there is no homes heating system in Guangdong province, right? So this is the situation. So we want to investigate the cold spell, right, occur in 2008, and what are the health effects. So we collect test data from these 3 cities during this period, right, the cold spell period, right, in these 3 years, and then compare with the number of deaths in 2008, right? The cold spell occurred in 2008. And this is the result, and this is the result. And you can see that actually in these 3 cities, and in these 3 cities, and the cold spell actually is associated with what is associated with the number of deaths, the deaths. And we can see that especially for the elderly, right, for the people in this age group 65 to 74 or greater than 75, right? So especially for people older than 75 years old, right? So the effect actually is very big. It's very big, right? And male and female both, right, affect male and female, and also the respiratory disease and cardiovascular disease, right? So this is we can see from this study the effect of cold spell. And we now know that low temperature, right, can cause death, right? How about the heat wave, the high temperature? So we also conduct a study, right, about the heat wave on mortality. And this time we select 4 cities, Nanxiong, Guangzhou, Zhuhai, and Taishan. Right? Nanxiong, Guangzhou, and Taishan. And the study period is 2006 and 2010. Right? And again, we collect test data, right, from these 4 cities during this period. Right? We collect the number, how many people die each day, right, during this period. Right? And we also collect temperature data, right, during this period. And we define the heat wave, right, the heat wave. If the temperature is at or above 95 percentile of the year-round daily mean temperature, and it lasts 2 consecutive days, and then we define it is a heat wave, right? So this is the result. And actually we can see that each heat wave actually is associated with the risk of a higher risk of mortality, right? This is the total, right? The risk of total mortality. And this is for cardiovascular disease mortality. And this is for respiratory disease. Again, we can see that for the elderly people, they are vulnerable population, right? Vulnerable population that more easy to be affected by the extreme temperature extremes. Right? So in addition to affect the chronic disease, next study shows the direct impact of temperature on infectious disease. I've used the COVID-19 as an example. And so this is a study, right? This is a study about the temperature or the meteorological factors and the COVID-19 incidence. And actually, this study is a collaboration between CUHK and UST. So we conduct this study in the middle of 2020, right? And at that time, actually, we do not have vaccine and we don't have drugs for the COVID-19 treatment, right? So we want to know whether the meteorological factors is associated with the transmission of COVID-19. So we collect the data, right? We collect around 2 million cases, COVID cases, and around 120,000 deaths from COVID, right? From 190 countries, right? And in this period, and we also collect the temperature data and meteorological data, right? And then we compare, because the data is from 190 countries, so the temperature vary in different countries, right? And then we compare whether the temperature is associated with the incidence of the COVID-19. So this is the result, and actually we can see that, right? And if the temperature is low, right, the transmission risk actually is high, right? And then the transmission risk actually decrease quickly, right, if the temperature increase, right? So this means that the temperature actually is associated with is associated with the transmission of COVID-19. We know that actually mainland China now is relaxing the COVID control method, and now it's winter, right? So actually it's not a very good timing for the relaxation. So I already showed you the direct impact of the temperature. So next, I will show you a study, right? So the indirect impact on public health. Indirect impact, that means the climate change, right? The weather, right? Change our environment, and then the environment affect our population. I will use the weather and air pollution, right? How weather affect the air pollution level, and then the air pollution can affect our population. So we know that this example is also related to what? Related to the COVID-19. We know that at the end of 2019, right, the first case was reported in Wuhan. And then the COVID-19 actually spread throughout China as well as the world quickly, right? So at the beginning of the 2020, and actually it is what? It is a coincidence with the Spring Festival holiday, right? So, and in that period, actually most cities in China actually were locked down, right? So there are no cars on the street, and most factories were closed, right? But unexpectedly, there's still haze pollution, right, in Beijing, Tianjin, and Hebei province. So a public feel confused, right? And they think maybe why there's no car and most factories were closed. Why still we have the haze pollution, right? So maybe researchers and scientists are wrong, right? Maybe the emission from car and factory may not be the cause of the air pollution. So to respond to the public concern, and Dr. Lin and Prof. Lau and Prof. Wang conduct a study. I was also involved in this study. So this study, the aim of this study is to differentiate the effect of meteorological effect on air pollution, right? So this study actually can answer public concern, right? And tell the cause of the unanticipated hazard pollution in Beijing, right, during the COVID lockdown period. So first we compare the air quality, right, between 2019 and 2020, right? So the blue color refers that the air quality actually improved, right? The concentration of PM2.5 decreased, and if the color is yellow and red, and that means the concentration increased, right? So from this picture, actually we can see that in 2020, actually in most provinces, right, the air quality actually improved. But for some provinces, or especially like Beijing, right, the quality actually what? The air quality worse, right? The concentration increased. So what's the reason? So we compare the weather condition, right, between 2019 and 2020. And for the wind speed, actually we can see that the wind speed in 2020 is slightly lower than 2019, right? And also the temperature is similar, right? But the humidity, right? The humidity actually what in 2020 is what increased quickly, right? It increased dramatically. So this picture just shows the purely effect of the weather condition, right? We assume everything is the same, right? It's the same between 2019 and 2020. And this is just the effect of the meteorological factor. And this is the effect of the wind speed, right? The wind speed. And actually we can see that the wind speed in 2020 actually what increase the concentration of PM2.5, right, in quite a number of provinces, include Beijing, right? And this is the effect of temperature. And this is the effect of the humidity, right? And actually we can see that what the humidity actually affect the air quality a lot, right? And this is the The left picture is about the effect of the meteorological factor, right? Include the wind speed and temperature and humidity, right? And we can see what we can see actually the air quality effect by the weather condition, especially in the Beijing, Tianjin, and Hebei provinces, right? So the right-hand side of the picture actually is the non-meteorological effect, right? Non-meteorological effect, right, on the air quality, right? And if we exclude the meteorological effect, actually we can see what? Actually, we can see the air quality in mainland China, right? In mainland China, actually improved a lot in 2020. So the conclusion of this study is, right, by excluding the meteorological effect, PM2.5 concentration substantially decreased, right, especially in Beijing, right? So showing that what the strict restriction, right, on human activity during the lockdown period indeed improved the air quality, right? However, the overwhelming the beneficial effect of emission reduction causing the severe hazer pollution, right? So this is the conclusion of the study. So this is the outline, right, I showed you before. So now we know that what climate change, right? Climate change actually have direct impact, right? The temperature extremes can directly cause death, right? Especially the vulnerable group, right? The elderly, right? Include both cold spell and heat wave, right? And also temperature can directly affect occurrence of infectious disease. I use COVID as an example, right? But actually a lot of infectious disease is related to the temperature. And also also weather play a critical role in air pollution, right? So climate change can affect our environment and then affect our population, our health, right? So this is the last slide, right? Just the implication for future climate, right? For future. So climate change actually is happening, right? We cannot wait. It's not a future event, right? So now we should have a short-term strategy. One of the strategies is establish the warning system, right? Because we have quite a number of the weather, extreme weather events. Another is to resolve the problem caused by the climate change, right? That means what? That means we need to improve air quality, right? Reduce the emission. And this is the resolve, the root of climate change. Okay, so that's my presentation.
Okay,
thank you.
Thank you very much, Professor Liu, for its impact on the health due to weather extremes as well as air pollution. Okay, so the next talk is by Professor Liu, yet again from the Division of Environment and Sustainability here. The title of his talk is Infrastructure Planning for a More Climate Resilient Urban Systems.
Okay, good afternoon, everyone. In this conference, we experience a lot of knowledge about the climate risk. And maybe I would like to try to talk about the solutions. Okay, we try to study solutions for this risk mitigation. In fact, we are able to create greater infrastructures. Okay, we can build a larger storage tank, okay, to mitigate the floodings. We can build super highways. Okay, we can also build very tall buildings. Okay, we can do a lot of things. Okay. However, but still, why we are worried about the climate changes, why we are starting to think about this is a problem. Okay, this is one of the experience I had before when I was in U.S. This is a traffic condition in Atlanta. Okay, within just 1 hour. Okay, so suddenly the street, the highways were blocked. Okay, and everyone has to drop their cars and went back home. Okay. This is a very unusual event in Atlanta that very tiny snow can interrupt the entire traffic system. Okay, so this is not because we cannot build a very high volume highway. This is something that we unexpected. Okay, so this is how we need to worry about. Okay, we have a big system. Okay, how we can manage it. Okay, so that's one thing that we try to raise attention is system failure. Okay, we may worry about one building in the event. Okay, but there is a more big grand risk. Okay, for the system. Okay, and this system failure is not visible to many of us. For instance, with climate change, you may find some food shortages. Okay, in the heat days, okay, suddenly there's power shortages. Okay, we never know this. Okay, until it happened. Okay, without the power, we will lose water as well, and you may have a problem with your food as well afterwards. Okay, so this is what we call a system risk. And this system risk is now very cascading, and we have to pay attention to this system failure. And more importantly, we are seeing that we question about our urban plannings. Okay, we have a poor managed urban plannings, and how we're going to take the advantages of urban renovation or urban regeneration to mitigate or to avoid this system risk. And more importantly, how we can scale up our solutions. Okay, we are talking one single building as a green building. That doesn't help our problem. Okay, how we can scale up our solutions for the entire city. Okay, so that's one thing we are asking in our lab. Okay, we have buildings, we have roads, we have all these great infrastructures. But when we put them together, we are not intended to create a problem of air quality or floodings or any global warming issues. We create these problems when we put them together. Okay, so how can we create a system that can have more benefits? Okay, climate resilient and carbon neutral, and try to avoid this unintended consequence as much as possible, if we can have a better idea about how the system will function. Okay. So here I try to bring up this what's emergency. Why we look at the systems. Okay. Emergency is something that are very different at the system level, that are different from the individual part. Okay, and we only see this in the emergencies when we have system views. Here we have an example. You see this. Here is a lot of phones here, but in fact it's a picture from President Obama. So this is we see is emergency. Something we have to look at when we have different scales. So that's calling something new research we try to identify, is that in fact we have a lot of disciplines work together on this problem. Okay, we have urban planning, we have urban engineer, we have civil engineers, but we cannot address this cross-scale complexities problems. But because now we have some boundaries, we look at the problems within our boundary and how we're going to address the problem. And we also have this environment side. Today we talk about heat waves, a lot of risks. But the gap between the risk to the final solutions, we see still there's a gap that how we address solutions. That's why we are trying to work on this converged science. Converged science, that how we're going to systematically understand and function in the system that are multi-scales, okay, they're interconnected, interdependent, and adaptive. In particularly, the system when we build, it's not just buildings, it's an interaction between humans and the engineered infrastructures. Okay, so we are interconnected, so that our demand affects our system and our system affects our quality of life. And this kind of interdependencies must be aware when we're managing our infrastructure. Okay? And more importantly, which is less understood, is what's the pathway for developing a livable, disaster-resilient, healthy, and sustainable systems from global perspective and individual perspective. Okay. What I mean by global perspective is how can we generalize the theory for planning the infrastructure systems, but individual city has our unique challenges. Okay? So how we customize this kind of theory for developing a more sustainable urban system like here in Hong Kong. Okay, so here I will use one example that we are studying is green infrastructure. Today, Professor Jia from Tsinghua University already mentioned this in China, and we have a customized study in Hong Kong. So the concept of green infrastructure, there's different definitions. We call sponge city in China, low impact development in US, water sensitivity urban design in Australia, or sustainable drainage systems in UK. There are different definitions. There are some similarity, there is some difference, but overall, the function of this new infrastructure is to mitigate a heat island and address runoff issues and water quality issues in the city. And these are typical facilities we can see, we can practice in the city. Okay? And China has ambitious goals that 80% of impervious area will be sponge city. And the same questions, will the 80% of impervious area in Hong Kong will be sponge? Okay? And Hong Kong would like to also try to increase the greenness in the city to provide more amenities to the citizens, right? So we try to answer the first questions here is, if we have 100% green roofs in the city, where can be cooled and how much can be cooled? Okay, so this is the study we did here. Is we look at in the column, if we have 100% roof greening, okay, what's the cooling effect in this area? Okay, so we can see in the Kuntung and in the northern areas, which is echo the study from our first speaker in this session. But if we're getting closer to the forest area, we have benefit from cooling. Okay, however, 100% green, is that possible? Okay, so our study further to question another problem: how much we need. Okay, the disappointing thing is that if we have a few investment green roof, doesn't help at all. We only get benefit, significant benefit, unless we have kind of tipping point. That means we must, until we get to this point, okay? So that we add more green roof, then there is a significant drop in the temperatures, okay? This is challenges. We need to scale up solutions. And now we need to talk with government that what policies we need to address this policy, or whether we should do this, okay? And we also conduct another study is runoff control in Hong Kong using the concept of low impact development. This is the funded project from the Guangdong province. So we select a small area first because we haven't have this model here in Hong Kong. And we calibrated the model, okay? So this is the data from real observations that we monitor the outflows from the communities, and we run our simulations. Further, we define the possible of low impact development so that we try to address, okay, where we can put these infrastructures. Okay, we try to add the buildings on rooftop on buildings, try add more bioretention, can catch the water, impervious areas in the cities as much as we can. We know that we have limited space in the city. Okay, so here is some quick findings from this practice. First, that the runoff reduction, the total runoff means over an event, the total runoff we can reduce is around 35 to 45%. Okay, but another finding is when the rainfall getting stronger, okay, the total volume reduction increase. Okay, that's good news. But the bad news is the reduction ratio decreases. Okay, so we cannot handle more water we get more water, but the facility cannot proportionally increase the same capacities. Okay, this total runoff. But the other point is the peak runoff. Okay, the peak is when we have a lot of water, there's a peak coming. So the behavior is very different from the total runoff reduction. So the potential is also similar. We can reduce around 30 to 45%, but the reduction volume for the all rainfall event, okay, is similar. Okay, so regardless how heavy the water is, okay, the maximum water we can reduce over the peak flow, okay, is the same. So this also recall a presentation from Professor Jia is actually low impact development of green infrastructure has some capability, but we still need to coordinate the development between green infrastructure and gray infrastructure, as well as our community development, okay, to maximize this kind of benefit. So this is one thing we are doing. We are still working on this because we only look at one community, how we can scale up this simulation to the cities, okay? So we are testing all the algorithms of this analysis. So overall, what we are doing in our lab is that we try to create this analytic capabilities for cities to explore the sustainability mitigation strategies. So overall, in the end, I tried to recall this important area is integrated assessment is becoming very powerful. No matter whether it's used by the government, it's also attractive to academia as well as the international organizations. In particularly for finance sectors, that we know there's a lot of risk, but how are we going to evaluate strategies? And how are we going to consider different options and the return on the investment for the societies? Okay, so this is the different role of integrated assessment model versus the climate models. So we need more kind of tools and strategies analysis for the city. Okay. So this is what we are doing. We try to catch up with the latest development. We are working on the water systems, urban plannings, and energy infrastructures for the Hong Kong cities in our lab. So the messages we try to share is we need to translate the climate change into climate impact. And we need to have more understanding about the impact of climate change on urban infrastructure systems. What's the impact? And the second thing is infrastructure systems are interconnected. Okay, we can only get more sustainability when we put them together. And here, the integrated assessment model are critical to equitable, economic, and effective mitigation solutions. Lastly, we should get the power of big data and a smart city from the investment to help us with integrated assessment modeling. All right, so that's what I'm talking.
Okay. Thank you very much for the talk. So that's why this morning is all about we need to work together. Okay, so this is the last talk, okay, by Mr. Pang from the Division of Public Policy here on city level and international collaborative project for climate adaptation in China.
Okay. Thank you for Professor's introduction. My name is Pan Ye. I'm a master student from the Division of Public Policy at HKUST. I feel it's my great honor to present the research of the international collaboration projects for climate adaptation in China, which is under the supervision of Professor Zhao Xiaofan. First, let me explain why we want to study the China's international collaboration projects for climate adaptation. First, there is an urgent need to improve the urban resilience worldwide, particularly in China. Managing climate change risk requires not only long-term mitigation efforts, but also immediate adaptation actions. But the adaptation governments falls far behind the mitigation worldwide. As for China, China is highly vulnerable to the adverse impacts of climate change, but the climate adaptation and risk management have remained much lower priorities on its domestic policy agenda than the climate mitigation. So given this context, there is an emerging government structure for the climate change adaptation in China. In contrast to the state-led top-down government structure for mitigation, there are more bottom-up local government-led initiatives in the area of climate adaptation, and many of them is in the form of international collaboration projects. because the international institutions can bring a variety of government resources, including the finance, the technical assistance, and the capacity building. But the current status of China's international collaboration climate change adaptation is still unclear. So we want to answer the question, what is the general landscape of China's international collaboration projects related to climate adaptation? We use the method of qualitative database to select and collect China's international collaboration projects on climate change adaptation, and followed by the classification of cases based on the following dimensions. The first dimension is the implementation level, including the city level, prevention and regional level, and the national level. The second dimension is adaptation sector, including water resource, disaster risk reduction, agriculture, forestry, biodiversity, and public health. The water resource sector refers to the response of the like droughts and extreme rain, such as water efficiency and flood control measures. And the disaster risk reduction sector refers to the prevention and control for the climate hazards, such as the sea level rise, the typhoon, and storm surge. The public health section refers to the mitigation of some public health risks caused by the extreme weather. And the third dimension is the function of international collaboration, including technical assistance and capacity building, infrastructure and service financing, research and risk assessment, and rule setting. For example, the draft adaptation plans. The first dimension is the form of international collaboration, including bilateral, multilateral, and transnational collaboration. And the fifth dimension is the spatial distribution. We collect the data according to the form of collaboration. And for the bilateral projects, we collected from the national communications and the biannual reports of UNFCCC Annex 2 parties. Annex 2 parties have an obligation to provide the financial, technical, and capacity building support to developing countries, including China. And the detailed information on the international aid program is recorded on the national communications and biannual reports of each country. And for multilateral projects, we collected them from the case database of Global Environment Facility, which is the financing mechanism of the UNFCCC, and major multilateral development finance institutions, including ADB, WB, EIB, and AIIB. For the transnational collaboration, we selected the transnational municipal climate networks that include members of Chinese cities. Okay, then I will introduce the results of our research. There is a total of 203 projects. 203 projects of the international collaboration, and at 43% is at the city level, and also 43% at the provincial and regional level, and 14% at the national level. This figure shows the number of projects implemented each year. We can see that the early international collaboration projects mainly at the provincial, regional, and national level. However, after 2005, there are increased number of projects and more international collaboration projects at the city level. For the dimension of adaptation sector, we can see that more than half of the projects focus on the water resources. China often has concentrated and heavy rainfall in summer, and therefore lead to the severe flooding. So there is an urgent need for flood control, and there is a large capital and technical demand for flood control infrastructures. So many cities want to strengthen their flood control capacities through the international collaboration projects. We also found that there are differences in the implementation level in different sectors. The project in the sector of water resource and disaster risk reduction is mainly at the city level. Because the climate adaptation needs are more urgent in these two areas, and the local governments are more likely to actively seek the international collaborations. And many of the adaptation measures in these two sectors are focusing on the infrastructure construction. So it is easy to implement at the city level. However, for the sector of agriculture, forestry, and biodiversity, the projects are mainly at the provincial and the regional level. Because adaptation measures in these sectors often need some nature-based solutions, such as ecological restoration and sustainable land and forestry management practices, so which often requires regional cooperation. And we find there are only 5 projects in the sector of public health. In the dimension of the function of international collaboration, the projects are classified into 4 categories. The first function is the technical assistance and capacity building. The second is infrastructure and service financing. The third is research and risk assessment, which is targets climate adaptation research and climate risk assessments. And the first function is rule setting, which is assist local governments to develop relevant plans and regulations to mainstream the climate adaptation. We think that providing technical capacity building and financial support is relatively low level of collaboration, which conduct target research and risk assessment and rule setting is a relatively high level of collaboration and are more important. We want to use the case of C40 to explain the functions. C40 is a transnational municipal climate change network, including 13 Chinese city members. It's established the city's 100 case study library to present the C40 member cities' solutions to climate change and organize workshops for experience sharing. And the C40 cities finance facility will finance the green infrastructures. And C40 also assists in Wuhan's climate change vulnerable assessment program, which performs the function of risk assessment. Finally, it also helps develop climate change planning for 5 Chinese cities. It performs the function of rule setting. This chart shows the classification according to the function. We can see that there is a decreasing trend from the low-level collaboration to high-level collaboration projects. And almost all the projects perform the function of technical assistance and capacity building, and 70% perform the function of infrastructure and service financing. But only 30% perform the function of research and risk assessment, and most of them are in the provincial, regional, and national level. And only 15% of the projects perform the function of rule setting. And there are 9 city-level projects involving 23 cities. For dimension of international collaboration, we can China has 66 projects. 66 bilateral collaboration projects on climate adaptation with 16 countries. We think the threshold for the bilateral collaboration is relatively high, and most of the cities involved in the bilateral collaboration are large cities. For the multilateral project collaboration, there are a total of 133 projects, with 16 funded by GEF, 70 funded by ADB, 28 by WB, 18 projects funded by EIB, and mainly in the forest sector, and 1 project funded by AIIB. we think the multilateral collaboration has a relatively low threshold, and it is only a form of international collaboration form for most small and medium-sized cities. And it's perform relatively single function, and the most mainly providing the loans for infrastructure investment. And for transnational collaboration projects, China has participated in 4 transnational municipal climate networks. The first is C40 and Making Cities Resilient, Global 100 Resilient Cities and Local Government for Sustainability. It's including 27 cities. And as I mentioned before, the climate networks undertake the multiple functions, including risk assessment and rule setting. And most members of the climate networks are large cities, which may widen the gap in the climate adaptation capacity between cities. Final is spatial distribution of the projects. The map shows the city level, the number of city level international collaboration projects that each city participates in. There are a total of 88 cities participate in at least one project, and 9 cities are involved in 3 or more projects. And Beijing participates in the largest number of 7 projects. There are spatial distribution of the cities. For the eastern, for big cities participate in more projects, and the projects are made in the sector of water resource and disaster risk reduction. And the projects perform diverse, there are diverse collaboration forms of the projects. For the small and medium-sized cities, most of the cities participate in 1 or 2 projects, and but the sector is diverse. And mainly in the form of multilateral collaboration. But there are some examples of small and medium-sized cities actively participating in international collaboration on climate adaptation, like Changde in Hunan province and Baise in Guangxi. I will quickly introduce the case of Changde. Changde was selected as sponge city pilot in 2015 and climate resilient city pilots in 2017. It participates in 3 international collaboration projects. For the driving force of cities participating in international collaboration projects, we find that the water frequency of the climate change and environment protection of the government reports of Changde is more than the cities at the same level. So we think the government attention is an important driving force for the cities to participate in the international collaboration projects, especially for small and medium-sized cities. Okay, finally is the conclusion and implications. For the adaptation sector that I mentioned, most of the projects focus on the water resource sector, but very few focus on the public health sector. As the extreme weather becomes more frequent, the climate adaptation projects that address mitigation of extreme weather should be increased, such as the establishment of heat wave warning system. And for the function dimension, only 30% and 50% of the projects perform the function of risk assessment and rule setting. And we think that Chinese cities should work more with the international agencies to develop relevant plans and regulations. And for the form dimension, there are 27 cities have joined the transnational municipal climate networks. And we think Chinese cities should be more involved in the climate networks as they can perform the diverse functions. And for the spatial distribution dimension, large cities participate in more international collaboration projects. than the small and medium-sized cities, which may increase the gap in climate adaptation capacity between cities. But the medium and small-sized cities can learn the experience from the cities like Changde or Baise to participate in more international collaboration projects. Okay, this is all of my presentation. Thank you.
Okay, thank you very much for the. Okay, so we'll just invite all the distinguished speaker here today. Mr. Pang, can you, please? So we are just one a little bit late, so we might just spend another 15 to 20 minutes. So now today we have quite a few talks on extreme climate impact on the vulnerable group. How do you working together, looking at systems, infrastructure, as well as what type of city has been working on climate change. If you look at the spatial map of Mr. Pan on the whole China map, it's less than 30% of the city are actually working on climate adaptation, as far as I see that map is concerned. So there's a lot of work still need to be done. So just wondering, any audience here have any burning questions? Yeah, Robert. Oh, maybe that one first.
Well, sorry about that, Robert. I have just a quick one. Anyway, I'm Alfred Lee. I'm a waterworks chemist, and I would just wish to thank to all for an excellent overview from all speakers this morning. Now, I will try to confine my questions to two the most, right? Hopefully. Now, first ones go to Billy, right? About is Billy here? Actually,
Billy, unfortunately, is not.
Right. Excellent.
Well, I will save the question for. Yeah.
Anyway, I will use up my.
That's very important, right?
I'll use up my backup. I would apply my backup question then, and maybe I will go for Professor Im. About the climate data. Now, you spoke of the misuse of the climate data could be equally problematic. Now, please give us some examples, right, about the severe consequence of the misuse of climate data. That would be the first one, and secondly, you might go to the Professor DELINA, right? Now, obviously, your project will be focused, mainly on the energy poverty in Hong Kong. Now, obviously, in your beginning of your presentation, you actually mentioned about, the water use as well. Do you believe that, we also have an equally, important, consequence, or situations of the water use poverty in Hong Kong as well? So that would be, my two questions. I will leave that, but in case I have a spare moment, I will save, some more. Thank you.
Thank you. Maybe, yeah, please.
Yeah, thank you very much for very important question, actually. Global climate model, we can easily access from the internet. So global climate model, for example, one grid size 100 kilometer by 100 kilometer, it means just one point to represent this whole area. But many impact assessment area, for example, agriculture, public health, hydrology, require much detailed information, but they just easy to get the global model data set. So just to apply such a coarse data for very detailed some impact assessment to research, then the result is not really reliable. I would like to say like that. Recently, even very fine scale regional climate model data also available, but of course it's more difficult to handle. But I would like to say you need to put some effort to understand and handle some data set. Otherwise, the climate change assessment result is not really reliable.
Even within the 1 kilometer resolution, different climate model would have quite a bit of.
And another point is, the Professor Jimmy Fong is raised very important issue as well. So climate model is always wrong. But still, so that's the reason we cannot really trust to one model. So that's the reason a lot of research institutes provide some many data set, and we need to understand the reliability and some, how to say, is a model skill. Without such a robust some understanding, we just apply some climate data to many fields, then I'm a little bit worried we may misunderstand really model behavior. Yeah.
I think Professor Yim's meaning is the uncertainty of the
uncertainty is very large. Yeah, uncertain, but we have to use that data. Otherwise, without physical model, we cannot really foresee at the end of the 21st century, right? But we should understand in a correct way some uncertainty range.
Okay, maybe let Professor DELINA answer the question first before you.
Yeah, well, thanks for the question. So the nexus between energy insecurity and water insecurity is there. It's in the extant literature. This is not necessarily what the research project is looking at. I think the question is actually very appropriate for Professor Zhongming Lu because he is working on the nexus of energy and water in urban environments. And his talk actually look at also at urban heat stress. But in terms of our project, we look at water and energy insecurity nexus, especially in terms of coping mechanisms. So the secondary literature suggests that vulnerable populations in Hong Kong, very limited data, especially those who live in public housing or private housing, I mean in SRUs, with lower income, they tend to cool themselves using public facilities. So they do their showering thing in public amenities. So that's where the intersection between energy insecurity and water insecurity comes in. But that's a very anecdotal evidence. So I think the question is actually for Zhongming Lu to respond.
Maybe I let Robert ask his question first.
Thank you. Maybe mainly for Mr. Pan Ye. We have had many excellent presentations this morning, for which sincere thanks. And I am left with indigestion. I am an accountant. I am working to try and influence companies to reduce their carbon emissions and adapt to climate change. I'm working with a think tank to try and influence what the government does. How do we take all the good information here and distill it into actionable items? Now, for science generally, we have on climate change, we have the IPCC produce these thousands of pages of reports, and we try and understand it from there. But that's global. For the local environment, people who are presenting here have much to say. Now, how does that feed through to government policy? How does it influence what companies do? How can we do that better in the future?
Yeah.
Hello, I'm Zhao Xiaofan. I'm assistant professor from the Division of Public Policy and supervising Mr. Pan Ye. So thank you very much for your question. So actually, we started this is the part of the bigger project on assessing China's governance capacity for climate change adaptation. So initially, we started with collaborating with the UK government. So there's a UK-China collaborative research on climate risk assessment funded by the UK government. So that research is trying to see what lessons we can draw from the UK or for international, different countries to help China. So as part of that research, we created a document, a final report, which was presented to the Ministry of Environment and Ecology. And we were also trying to, and part of that research, the policy suggestions, recommendations, also fed into the creation of the latest 2030 climate change adaptation strategy of China. And after that, that project actually officially ended. But now, Pan Ye and I were trying to, apply for more research funding in the future to conduct further research. At this stage, where I think we wanted to move from the macro level to the micro level. So now we're looking at more like regional, provincial, or even city level projects that Chinese cities are conducting at this moment. Well, so we haven't really figured out the channel through which we can influence policy making, but at least as a consult, I do some consultancy work for C40. So as part of for that role, I was able to participate in a lot of workshops to train Chinese cities, which are the C40 members, to influence their adaptation planning. So hopefully, I'm also very happy to, first of all, distill my thoughts, what I learned from these conferences, and to report back to C40 cities. I'm sure a lot of these research results would, benefit them in the future. Thank you very much.
Okay, thank you.
Maybe I can
please.
have a comment on this. I think there are many ways to influence the policy. For example, organizing conference. Yesterday, there are many officers participating the conference, and they expose to this kind of information and receive this kind of information. I think this is organizing conference and invite officers to join the conference, and they know the information, and this will also influence the policy development.
Of course, one way is through these type of platforms. As we mentioned earlier, we'll write up a lot of your questions and comments and some of our policy recommendation, a summary report to the government, in particular to the Environmental Protection Department as well as Hong Kong Observatory. So, Mr. Nam.
Professor DELINA, you have filled a very important gap, I think, for the Hong Kong society. I think the government is not thinking about the poor people, not thinking about them at all so far in terms of reacting or responding to climate change. I have tried to convince them that the poor people should be provided with a minimum amount of electricity free of charge, but they think it is nonsense. So please do work much harder on your project and speak much more to a wider community. And of course, please record this in your summary of the conference.
Absolutely.
Yeah. Actually, I think there is a big problem in the future decades for the poor people, apart from the vulnerability they are already facing. We now know that electricity price will go up. And then as we transition from conventional energy source to hydrogen or renewable energy, because of the incompatibility between the demand and supply of new form of energy, I think the electric energy price will fluctuate widely. And so during the transition, the poor people really can't survive. So there must be a way worked out together with the government to find a way of ensuring that they could survive in spite of the great fluctuation in energy supply. So I can't really find a question for you because you're filling a very important gap. So if I have a question, I will ask you, how could you do better to let people know that there is a problem? Yeah.
Well, thank you so much. Yeah, we will do our best to do our impact work as we move forward in this project. But I just have to make mention that we are not actually only looking at the people living under the poverty line, so economically poor, but we are also expanding actually to other vulnerable groups. And at the moment, we have identified about 10 vulnerable groups, and those living below the poverty line is one of those 10. But yeah, thank you so much for your encouraging words. We will work very, very hard to translate our research outputs into impactful policy recommendations.
Yeah, maybe Zhongming, you have any input as
I agree there is such kind of trend in the future, in particularly when we plan this infrastructure and how we're going to provide incentives or policy support for vulnerable communities. So in our study, we also try to quantify the severity of this cost to the different communities. So when we plan different pathways, so which pathway has the minimum impact on the vulnerable communities is also considered in our system planning. So this is what we try to include in our integrated assessment models.
Okay, with that, okay, thank you very much due to time limitations, and thank you very much for the very enlightening talk of our speakers. I will leave the last word to our chief organizer, Alexis Lau, to wrap up today's presentation.
First of all, thanks so much for staying behind until already 1:20, and I assume a lot of you may have drums in your stomach. But I actually find that I gave a very difficult task for myself, because I put up a title for my roundup, but then actually the title I have to explain it a little bit. So bear with me a little bit in terms of time, but hopefully it should all be finished within 10 minutes, okay? Because yesterday, actually, I was in workshop B talking about how do we prepare for the unknown? What are the unknown risks, okay? Well, if I can tell you what is the unknown risk, they are not unknown. So there will not be answer for that. But how do we prepare for that? This work is actually working with one of my PhD students who is in the audience right now. But anyway, the important thing that I want to highlight is the IPCC in 2012 put up this framework, which I think most people use to look at climate risk, which is a combination of the hazard, vulnerability, and exposure. Okay. Here, with this, they also talk about setting up early warning system. This is their recommendation in the Working Group 2 report. On a lot of things, they always talk about early warning system, early warning system, early warning system. But if you have no idea what are the risks, how can you get yourself warned? Because you don't know what to monitor. So what are the type of things that you need to monitor has a lot to do with your understanding of where the risks are. Okay? So we have to understand what are the risks. So in their talk about this early warning system, they actually say it's important to identify the risks as well as establish decision-making criteria. Once you have that, then you can start doing the early warning system. Okay? But sounds okay, but it's difficult because a lot of the risks are highly nonlinear. We now know that, well, I think there's a lot of talk this morning about heat. Heat can actually become drying the land, and it creates fire. And it changed the land use completely. I support Professor Im's comment, all models are wrong. By definition, models are simplification, but models are very useful. If you think that models are wrong, then they are not useful, I also would disagree with you. Models are very important. Without them, you cannot study nonlinear interactions. However, I think this is very important for us to understand. Model cannot be relied on to give you this type of very complicated nonlinear interaction. It's difficult. Zhongming talked about system-integrated modeling. I guess when we get more and more into that, we can have better and better simulation of those effects, but not at this point. We talk about heat wave. I don't know how many people know about the so-called heat wave of 2003. How many people died during that year or because of this heat wave? Wow, I think these are really in the field. But really, a lot of people don't understand. But what do they mean by a heat wave? This is the record, okay? The so-called heat wave is that the temperature in Europe get to about 30 degrees. Okay, for people here, what heat wave, right? But if you look at their historical temperature, it's about 20-some degrees. And then for 2 weeks in 2003, it get to 30. And, well, you may say, what's the big deal? Well, according to the early report, they say about 15,000 people died in France. And then subsequently, there are more research on it. And the final one, more recently, is 70,000 people died. Okay? And this is because the way people are advised is wrong. Because they were advised if the weather is hot, stay home. But those homes, they don't have air conditioning. And so a lot of the older generation actually stay home and die in their apartment. Okay? And this is important to learn because this is not something you can't manage with a lot of money. Actually, by 2009, a similar heat wave happened. Much, much less death is reported because the system now know how to respond. Basically, cooling center is set up, people are advised to move there, and so on. So having a early warning system with decision making is very important, not just know it. You need to have followed the whole chain of command. Okay? So this is an important thing. Okay, this talking about nonlinear risk. I always like to use this example. I have a son studying in Chicago. Not studying, now working. So I went there quite a lot and then noticed reports talking about roads which have potholes open up during the winter, and it's getting more and more. What happened is the ground level, groundwater. Most of the time before, the groundwater basically freeze and thaw once. With climate warning, they actually get the freeze and thaw much more often, and it create pockets under the road. And then when heavy vehicle go above it, it will break through the road and then fall down. And it creates some accident and some casualties, okay? But again, sorry, modeler cannot do that. It's very difficult for model to predict that without knowing that before. Okay, so how do we try to predict this? Well, if we cannot predict it, I would recommend, well, we search for it. The other thing is, even if we know something, whether we can transmit that information, let others know. This is an example of Hong Kong. In 2017, we have a typhoon around here, which killed a number of people in our car parks. Well, in Macau's car park. Okay? The reason being the car owner go underground car park and try to pick up their car when the typhoon rain was heavy. Unfortunately, they can't get out in time. 2018, we have a much stronger storm, Mengqian. No one died in Hong Kong or in this region because of that, because everyone remember what happened in 2017. Unfortunately, in 2022, which is this year, same thing happened in Korea. Well, if Korea look more at our news, maybe they can say with this example, and also probably the example, well, many other incidents. So how can we deal with this? Is we need a platform to share this type of information. Okay? So we think that to deal with this, we probably use big data. I think a lot of people talk about using big data. Right now, because there are news being reported everywhere, we can use big data method to really gather climate impact and risk stories. Okay, go around the world basically doing this, and then put it in a what I would call a CARE risk database. Categorize them according to different area, different type, and then depending on what type of organization or responsibility you have, you may get into this type of place and try to understand what are the potential risks for your area. And hopefully, we can even crowdsource the risk. If you set it up right, people can actually help input things that you don't search, okay? But this is something, is a concerted effort. So I'm not bothering you with the technical detail, but basically is using natural language processing, looking at the news, pick up main points, and try to distill the information down into groups. Okay, I will skip all this technical thing. Is try to identify search keywords, search efficiency, do the looking at the title, first paragraph, entire article, identify particular thing, and then try to look at different risks. But here are some examples. You can see how like the heat wave can impact the energy supply chain, as well as sometimes even for the particular heat wave, this is quite famous now, I think. At that time, because of the energy cutback, they want to use more of the coal. But the coal cannot be transported by the boat or by the train because of heating. So there are multiple failures, which Zhongming has talked about a little bit. Okay? But one other thing, maybe, I kind of find this interesting, is a lot of things you may not think about. There's 3 different incidents. Okay, one in Hong Kong, banquet. A lot of trees are brought down. Bees are flying around and bite a lot of people. And then in Egypt, scorpions come out of their place because of their habitat are being flooded. And then there are some snakes coming out because of flooding. So these are, again, I'm sorry for the modeler. We are not going to do this. But I think this, I'm not saying that we should worry about scorpions or snakes here. But I think in every habitat, there probably are some species that may have impact. Like, well, we can think about our wild boar or other species for different places. But these are the things that we probably are not prepared for right now. So I'm not going to exhaust the list because I always highlight these are unknown risks. Okay? So what I think should happen is that, well, we are working on the first part, how to identify the news stories, try to categorize a risk database, and then hope to get a community effort to enhance the risk database so that different groups looking at this, they may think about their own vulnerability as well as exposure for those risks. But also very important because a decision-making criteria has to be set to respond. To know the risk, we know heat wave kills. But if we don't have a system to work, then it doesn't work. So we think that any organization or government that need to address climate change has to establish a very high-level CARE office. One very important thing is that this office must be free from the day-to-day operational needs. Right now, most of the climate office or climate change risk office are also dealing with day-to-day safety operation. This is unfortunate because day-to-day safety probably are related to things that happen very often. Climate risks are low probability, high impact, which are very different. If you ask people to look at both, then it's just natural that they will focus on the high impact or more frequent situation. So if the frequency of occurrence remain that way, maybe that's right. But our projection is that the high impact cases will increase in frequency, and we have to be forewarned by it. So it's important for us to really think about that. Okay, and this cannot be a one-time exercise. So we need a dedicated office to look at it. I think for each organization that has large stakeholder or large impact population, I think it would be reasonable cost for them to spend that effort, okay? And their report should be directly going to the decision maker. Anyway, yesterday I was putting this as my afterthought, saying that, well, people are talking about the 8.5 degree world. 8.5 degree world is up to 5.5 degree warmer. I don't know what that look like, but a 6 degree colder world is something like this, which the land use is completely different from what we know now. Okay, so we cannot expect the 8.5 scenario is the world that we are used to. Okay, the land use, everything probably will look very different. And according to IPCC, what we do in the next 20 years is quite important to make sure whether this could happen, not will. Okay, I still highlight could. Okay, so this is my roundup. Huge challenge ahead, and unfortunately, I think many will suffer. I think it's just an acknowledgement that I don't think we can settle this quickly. And also we will stumble along the way in the sense we won't get it quickly or directly. We probably try it here, right there. But I actually, these are two of my authors, which I really admire. One is David Christian. He's talked about collective learning. Why? Human, I think some of you may not agree. Humans, or sapiens, is the most collaborative species on Earth. Think about it. Maybe you think we argue, we fight so much. But everyone depends on people you don't know, and also not just people now, but people who have lived 100 years ago or even 1,000 years ago. We rely on each other. Our progress is a collective learning process. The other thing which Yuval Harari talked about is why we were so successful is our ability to collaborate very flexibly. We can change our collaboration in a relatively short period of time. Compared with genetic collaboration like insects, we are much more flexible. And that can be demonstrated, I think, best during COVID. Actually, COVID helped me in the teach of sustainability. Before COVID, when I talk to students, most of the students think that it's impossible for the world to change. Even small things, people will argue, fight, and doesn't do anything. But I think COVID showed that the world can change. If in 2018 you ask me whether I would believe in the type of restriction come in like COVID. I would not. But everyone has seen what happened. I think the point there is the system and the rules can be changed. What we have to do is to have a good articulation as well as the right incentive. Because answering Robert's question, I think incentive is so important because without the right incentive, it's difficult. But with the right incentive, scaling with business, I think we can start to address the problem. Okay? We also should not expect solutions that will cover everything. We should expect solutions that help along the way, giving you a general direction. Okay? And this is our way of adaptation and evolution throughout human history. So I think this is important to understand, and when you see problem with some of the solution, don't shoot it down. Think about it is along the right direction. Every solution probably has some limitation, but overall, can they deliver some small step in the right direction? Okay, and I think goal-oriented is important. Coming back to climate change, I think we are having some goals being converged. Okay, our 2050 zero carbon goal, with most of the other countries, including China, has this zero carbon goal. Those are being converging. And with the converging of goals, I think the incentive system are being established and being argued. And that's also a very important process. But I believe once that happens, the direction will accelerate. Okay? What we need to do is, again, don't hope for a single solution. We need to be agile. Okay? We need to understand and kind of scan what is happening, always prepare to change our vision, our plan, as well as I think we can only hope for minimized damage instead of hoping for no damage. Because I think perfect is sometimes the enemy of good. Sometimes I think arguing too much about, oh, this solution has this minor or some defect, that solution has this defect, at least that may not be the best way to go. That's my opinion. Okay? But here, I think I also want to say a lot of work needs to be done. And this, particularly because this is an academic day, and I understand a lot of research students are coming. So I want to say this is actually a good opportunity for you, okay? Imagine you are the mask maker in 2018, knowing that COVID-19 is coming, okay? But I think if you are working on this type of incentive, this type of system, actually you're similar to that. Like students who are studying ESG in 2015, okay? I think they know how much demand they are right now. But this demand will be there because this is what the world really needs. So I think what I can say in rounding up is we hope to have more CARE conference so that we can stay on top of the issues, technology, solutions, and most importantly is the collaboration. That's the strength of our species, and only through that we can deal with this problem. Okay? Thanks so much for staying for so long.